Nutter butter cookies are built through a remarkable factory process that transforms simple ingredients into an iconic peanut-shaped snack. Precision mixers whip peanut-rich dough, massive rollers sculpt the signature ridges, and high-speed ovens lock in that golden crunch before peanut butter filling units press each sandwich together. In this documentary, we'll follow every stage of this engineered workflow and reveal how millions of identical Nutter butter cookies are made daily. The production of Nutter butter cookies begins with the precision blending of dry ingredients that form the base of the peanut-flavored dough. Large stainless steel silos hold raw materials such as enriched wheat flour, sugar, baking soda, and salt. Each of these components is metered through automated valves into a high-capacity ribbon blender. The flour is conveyed pneumatically, flowing through stainless steel tubing under constant pressure, ensuring no clumps form during transit. Sugar and leavening agents are simultaneously dispensed from adjacent hoppers using vibratory feeders. Load cells under each hopper monitor exact weights, adjusting feed rates in real time to maintain the precise recipe ratios. Once inside the ribbon blender, dual helical blades rotate at offset speeds to fold, tumble, and shear the dry ingredients into a fine, uniform mix. The entire process is enclosed to eliminate any moisture intrusion. A dust extraction system pulls excess airborne particles into a central filtration unit, preventing accumulation inside the mixer housing. After 3.5 minutes of blending at 160 revolutions per minute, the dry mixture reaches a consistent particle size and is released through a pneumatically controlled bottom hatch into a transfer hopper below. From there, the dry mix enters the wet addition stage. In a separate vat, partially defatted peanut flour, natural peanut butter, emulsifiers, and invert sugar syrup are heated gently to 35 degrees Celsius. The peanut butter is stored in heated jacketed tanks to maintain its viscosity, and gear pumps push it through heat-trace stainless pipes into the mixing chamber. There, high shear paddles integrate the wet ingredients into the dry matrix. This continuous mixer, fitted with torque sensors and temperature monitors, carefully kneads the ingredients into a cohesive dough. Dough temperature is critical and maintained below 27 degrees Celsius to prevent the oils in the peanuts from breaking down or separating. The resulting dough, now thick and slightly tacky, exits the mixer through a rotary discharge valve and drops onto a conveyor leading to the sheeting line. Before reaching the sheeter, the dough passes under a cross-roller system that pre-presses it into slabs of consistent height. These slabs feed into a multi-roll sheeter consisting of 2 chrome-plated rollers turning in opposing directions. The gap between rollers is set to millimeter precision, compressing the dough into a continuous sheet with uniform thickness, typically around 6.5 millimeters. Sensors along the line scan for inconsistencies in thickness using laser triangulation. If deviations exceed tolerance levels, actuators automatically adjust the roller gap to compensate. The dough sheet then travels under a chilled air tunnel, which slightly firms the surface to prepare it for cutting. This conditioning process improves the cleanliness of the next step. Rotary die cutting. The peanut shape of each cookie is achieved through a custom rotary mold affixed to a cutting drum. As the dough sheet feeds beneath it, the die presses downward with calibrated pressure, stamping 2 interlocking halves of the iconic peanut shell design per cycle. Embedded rollers on the die drum imprint the ridged surface pattern, adding texture that resembles the veined shell of an actual peanut. The cutouts are separated from the waste dough using a vacuum lift system that raises the stamped shapes and transfers them to the next conveyor, while the remaining dough trimmings are immediately recirculated back into the sheeter. Before baking, each cookie half is inspected by a vision system that uses high-resolution cameras and infrared scanning to verify shape integrity and detect defects such as torn edges, incomplete ridges, or excessive thickness. Acceptable pieces pass through a gentle vibratory aligner that spaces them uniformly onto a mesh belt oven conveyor. The baking process is conducted in a continuous tunnel oven that spans over 30 meters in length and is divided into multiple independently controlled zones. The initial zone applies intense bottom heat from gas-fired burners, causing rapid expansion of the dough as moisture begins to evaporate. The cookie halves rise slightly as steam forces air pockets to form within the dough structure. Midway through the oven, radiant heat from the top elements sets the surface and completes the Maillard reaction, giving the cookies their golden brown hue. Precise humidity control ensures that the cookies develop a firm shell without drying out the interior too quickly. Air velocity within the tunnel is controlled by variable speed fans, directing heat flow uniformly across the belt. Temperature ramps gradually from 180 to 220 degrees Celsius across zones to create a consistent bake profile. A moisture probe at the end of the oven verifies that the final moisture content is below the target threshold, typically under 3%, ensuring crispness and shelf stability. Once fully baked, the cookie halves emerge from the oven onto a cooling conveyor, where forced ambient air reduces their temperature from over 100 degrees Celsius to below 30 degrees within 7 minutes. The cooling system features perforated belts and laminar airflow to prevent condensation or warping. Sensors continuously monitor belt speed and air pressure to maintain cooling efficiency and prevent heat buildup. After cooling, the cookies enter the sandwiching system. This portion of the line operates with synchronized precision, pairing two halves perfectly while injecting the peanut butter filling. The filling itself is prepared in a separate mixing system where partially hydrogenated vegetable oil, powdered sugar, peanut paste, and salt are blended under vacuum to remove air bubbles. The result is a smooth, viscous cream held at a stable temperature of 25 degrees Celsius. The cookies pass through an orientation station where overhead cameras identify the top and bottom side of each piece, ensuring that the correct ridge surfaces face outward after sandwiching. Each bottom half is placed into a moving tray slot on a high-speed indexing belt. A servo-driven nozzle dispenses a precise dollop of peanut butter filling, measured to within 1/10 of a gram, onto each base cookie. The top half is then picked and placed using robotic arms that utilize vacuum suction cups to align and gently press them into position, forming a complete sandwich. The filled sandwiches then enter a compression conveyor, a narrow belt segment where overhead rollers apply gentle pressure to spread the filling evenly to the edges. Excess cream is wiped clean by a pair of rotating brushes, and the completed cookies proceed to quality inspection. A second vision system confirms alignment, checks for cracks, and ensures that filling distribution meets visual standards. Those that pass inspection continue to the enrobing station, where a light mist of edible release agent is sprayed to give the cookies a slight sheen and reduce stickiness during packaging. Next comes the staging area for packaging, where cookies are grouped into uniform stacks by a combination of paddle sorters and pneumatic pushers. Each stack is weighed on in-motion check weighers calibrated to detect even fractional discrepancies. From here, they're fed into a high-speed flow wrapper. The wrapping film, pre-printed with branding, is unrolled and drawn through a former that shapes it around each stack. Heated jaws seal the ends, while a fin seal roller crimps the back, creating an airtight pack in under 2 seconds per unit. Once the wrapped and palletized cartons leave the final packaging zone, attention shifts to replenishing the production line's front end with precise and consistent ingredient delivery. To maintain uninterrupted operation, the ingredient handling system functions in a closed-loop cycle that refills raw materials such as flour, sugar, peanut paste, and oils into their respective silos and tanks. These materials are transferred through a combination of pneumatic conveyors and positive displacement pumps. Each route is designed with stainless steel tubing, fitted with inline particle sieves, magnetic traps, and backflow prevention valves. Flour is delivered from bulk storage tanks via aerated hoppers that loosen compacted particles for smooth flow. Once aerated, the flour travels through a vacuum-driven conveying system into holding silos above the primary mixing area. These silos are equipped with rotary-level sensors and internal agitators to prevent compaction. A rotary airlock feeds the flour into weigh hoppers situated on high-precision load cells. This entire process is orchestrated by a PLC-controlled batching system that ensures real-time synchronization between material demand at the mixer and supply from the storage system. Sugar and baking soda are stored separately to prevent cross-contamination and clumping. Sugar is conveyed using an enclosed tubular drag chain system, which moves granules gently to reduce dust formation. Each granule flows through a vibratory sifter before reaching the surge hoppers. Baking soda and salt follow a similar path but require desiccant filtered air to maintain dryness. These ingredients are often pre-blended in intermediate mix stations, reducing the number of feeds needed for the main batch mixer. Meanwhile, the preparation of the wet phase for the dough involves specialized handling of peanut-derived ingredients. Peanut paste, partially defatted peanut flour, and stabilizing emulsifiers are stored in heated tanks equipped with slow-turning agitators. These tanks are temperature-controlled using a hot water jacket system, ensuring the peanut paste remains fluid without overheating, which could damage flavor or consistency. The paste is transferred through a tri-lobe pump that maintains a consistent flow rate into the dough blending chamber. The temperature and viscosity of the peanut paste are monitored continuously using inline viscometers and thermal probes. As the paste enters the wet mixer, it is joined by invert sugar syrup, which acts as a humectant to balance moisture in the final cookie texture. This syrup is made on-site by hydrolyzing sucrose with citric acid in jacketed tanks, then neutralizing and filtering it before holding in reserve tanks. The mixing of wet and dry ingredients occurs in a two-stage continuous mixer, where the first stage initiates hydration and the second stage completes dough development. This system utilizes a co-rotating twin-screw extruder adapted for dough handling, not extrusion. Within the extruder housing, the screws rotate at variable speeds, pushing the ingredients forward while shearing and folding them together. The barrel is segmented with independent temperature controls across sections. Water jackets and temperature-controlled zones allow for precise heat exchange, which keeps the dough pliable but prevents premature cooking. Dough consistency is measured in real time using torque sensors, which correlate mechanical resistance with texture, allowing automatic adjustment of hydration levels if the dough thickens beyond target thresholds. Once the dough reaches ideal parameters, it is discharged through a diverter valve into a hopper that feeds the sheeting line. The sheeting process uses 3 reduction rollers arranged sequentially, reducing the dough in controlled stages. Between each roller, infrared sensors detect thickness, while air knives blow off flour dust generated during rolling. The final thickness is achieved with a precision gap set by servo-driven actuators, holding the tolerance within plus 0.1 millimeters. Dough temperature is also maintained here, with cooling fans blowing across the belt to prevent softening that would distort cookie shape during cutting. The dough sheet then enters a rotary cutter system consisting of 2 key components: the engraved die roller and the anvil roller. The die roller features etched cavities shaped like the Nutter Butter's iconic peanut shell halves. These cavities not only cut the dough, but emboss the distinctive ridges. The anvil roller provides a hardened steel backing that ensures each cut is clean and consistent. This mechanical action happens in a continuous loop, with the dough sheet moving under the cutter at over 20 meters per minute. The trimmings that surround the cut shapes are not wasted. A vacuum extraction system collects the excess dough and redirects it back to the pre-sheeter hopper, where it is reintegrated into fresh dough. This recirculation is time sensitive, and the amount of recycled dough is metered carefully to ensure it does not exceed 15% of the total, preserving texture and integrity. After cutting, the raw cookie halves pass through a transfer bridge leading to the oven infeed. Before entering the oven, cookies pass over a depanner belt, where any pieces that have stuck to the conveyor are gently lifted and repositioned. The belt itself is made from food-grade mesh that allows hot air to circulate upward during baking. The cookies enter a traveling tunnel oven, which is segmented into multiple thermal zones, each controlled by an array of thermocouples, modulating gas burners and airflow dampers. The first zone of the oven promotes rapid bottom heating to create steam and lift the cookie slightly. This helps create internal porosity without allowing the structure to collapse. The next zones gradually increase the top heat, activating Maillard browning and allowing caramelization of the sugar peanut matrix. The final zones focus on moisture extraction, where convective airflow is intensified. Multiple exhaust fans evacuate humidity, and infrared sensors track surface browning levels. At the end of the tunnel, cookies descend a slight ramp onto a mesh cooling conveyor. The ambient cooling section is designed for uniform thermal reduction. To prevent thermal shock or warping, airflow is introduced from below in a laminar pattern. This ensures that the cookies cool gradually and evenly, allowing the interior to fully set without over-drying the outer surface. The conveyor speed is adjusted depending on ambient factory conditions, using data from thermal imaging cameras mounted overhead. As cookies reach ambient temperature, they enter the filling line staging zone. Each cookie half is guided into a high-speed orientation system that aligns them, using mechanical rails and vibratory sorting bins. This ensures all halves are positioned identically before the filling is deposited. The peanut butter filling is pre-blended in a vacuum mixer to remove entrained air and ensure smooth texture. The filling mixture includes fine powdered sugar, peanut paste, stabilizers, and emulsifiers, all homogenized to produce a cream with low moisture and uniform spreadability. The filling is transferred into positive displacement metering pumps, which drive it through jacketed stainless steel piping to a manifold of precision nozzles. Each nozzle is servo-driven and synchronized to match the conveyor speed of the cookie halves below. As the base cookies pass under each nozzle, a perfectly round bead of filling is extruded. The shape, weight, and height of the filling are controlled within 1.5% variation. Immediately afterward, a robotic placer system equipped with vision guidance picks the matching top cookie halves and places them over the filled bases. The arms are mounted on gantry systems that allow high-speed XRY movement, and each arm uses vacuum suction with pressure sensors to ensure gentle contact. Once paired, the sandwich cookie moves into a compression zone. This segment uses dual belt conveyors running at different speeds to exert horizontal pressure, spreading the filling evenly to the edges without squeezing it out. Post-compression, the cookies pass under a camera array that scans for alignment precision. Any cookies where the top and bottom halves are not concentric or where the filling is off-center are automatically diverted. Cookies that pass inspection proceed to the enrobing line, where a fine spray of release agent is applied. This oil mist not only enhances the appearance, but reduces friction during the packaging stage. After the wrapping stage, each sealed package of Nutter Butter cookies proceeds down the conveyor toward the cartoning system. This section of the factory is fully automated and synchronized with upstream processes to maintain a consistent flow rate. Packages enter a servo-driven collation unit that arranges them into specific pack patterns. Optical sensors monitor spacing and orientation, triggering a pusher arm that nudges each wrapped unit into lanes formed by stainless steel rails. Once a complete group is assembled, for instance, 6 or 12 units, depending on the packaging format, they are released into a drop chute that feeds a cartoner in-feed bucket conveyor. Cartons are erected automatically from flat blanks using a high-speed forming machine. This device employs a rotary vacuum arm that picks blanks from a magazine and transfers them to a forming station. There, mechanical plungers push the blank into a forming pocket, while adhesive is applied via hot melt glue nozzles to secure side flaps. Within less than a second, each blank becomes a rigid box, ready to receive product. The formed cartons are synchronized with the in-feed conveyor, where filled buckets tilt forward, gently sliding the wrapped cookie packs into the cartons using gravity-assisted chutes. Once the packs are loaded, top flaps are closed and glued shut using the same hot melt adhesive system. A compression belt ensures the glue sets firmly before the cartons exit onto the next conveyor. At this point, thermal inkjet printers apply alphanumeric codes onto the cartons, identifying lot number, production time, and expiry date. These codes are read back by vision verification cameras to ensure legibility and data integrity. If a misprint is detected, the defective carton is diverted onto a side reject lane. After code verification, filled cartons move into the case packing zone. Here, several cartons are grouped together into shipping cases. A case erector forms corrugated boxes from flat stock using vacuum cups and mechanical plungers, similar to the carton formers but on a larger scale. Once opened and set into shape, the corrugated cases are advanced to the loading station. Robotic arms equipped with parallel grippers pick up multiple cartons simultaneously and lower them precisely into the open cases. The configuration of cartons inside each case is optimized for pallet stability. For example, cases may be loaded in a 2x3 configuration, rotated 90 degrees between layers to create interlocking strength. Once loaded, the top flaps of the cases are folded shut and sealed using either hot melt glue or pressure-sensitive tape, depending on the production run. Each sealed case then passes over a weight verification scale, which confirms the presence and correct number of internal cartons. Cases that fall outside acceptable weight ranges are automatically rejected and redirected to inspection. Acceptable cases proceed to palletization, where a 6-axis robotic palletizer orchestrates the stacking of cases onto wooden or plastic pallets. The robot uses a vacuum end effector designed to grip the top of each case while aligning it using onboard laser distance sensors. Each layer is carefully aligned, and layer sheets are inserted between rows when necessary to enhance load stability. Pallet patterns are programmed into the robot's control system, which can adjust automatically based on case size and shipping requirements. Once a pallet is fully loaded, typically reaching a height of around 1.6 meters, it advances to the wrapping station. Here, the pallet enters a turntable stretch wrapper where a roll of polyethylene film is spun tightly around the pallet while the turntable rotates. Tension on the film is dynamically adjusted to accommodate varying pressure across the load. The wrap provides dust protection and containment strength for transport. A film cutter and wiper arm secure the final edge of the wrap without manual intervention. Now completed, the wrapped pallet is conveyed to a finished goods staging area. Before entering storage or shipping zones, the pallet passes through a barcode scanning tunnel. This tunnel reads the case labels on all visible sides and links the data to the central manufacturing execution system, allowing full traceability. At this point, the production cycle for a batch of Nutter Butter cookies concludes, and attention returns to the upstream processes that prepare the unique peanut butter filling. The filling itself requires a continuous blend of peanut paste, fine sugar, and specific emulsifiers. The process begins with the controlled heating of peanut paste inside stainless steel jacketed vessels. Each tank is fitted with an agitator driven by a gear-reduced motor, operating at low RPM to maintain homogeneity without incorporating air. The paste is drawn from bulk totes using diaphragm pumps and delivered through sanitary hoses into the blending tanks. Meanwhile, dry ingredients are introduced via vacuum transfer from nearby storage silos, entering the tank through a top-mounted hopper fitted with a rotary valve. The blending tanks are connected to a programmable logic controller system that regulates ingredient proportions based on real-time weight measurements. Load cells beneath the tanks continuously monitor ingredient mass, allowing precise dosing. Once all ingredients are present, the mixture is agitated under controlled temperature, typically around 30 degrees Celsius, to ensure that the sugar dissolves evenly and the emulsifiers disperse completely. This heating phase lasts about 10 to 15 minutes. After blending, the peanut butter cream undergoes homogenization. The entire mixture is pumped through a high-shear inline mixer equipped with a rotastator assembly. As the mixture passes through the narrow gap between the rotating and stationary components, it experiences intense shear forces that break down any remaining particles and eliminate microaggregates. The result is a silky, uniform texture with excellent spreadability and no visible granulation. The homogenized filling is then cooled through a scraped surface heat exchanger. Stainless steel blades rotate inside the exchanger, constantly removing the filling from the cold inner wall while maintaining a thin film for rapid thermal transfer. The goal is to lower the temperature of the filling to 25 degrees Celsius without forming crystallized sugar structures, which could cause grittiness. This process preserves the optimal viscosity for depositing the filling onto the cookie halves. The cooled cream is transferred into intermediate storage hoppers, which feed the depositor heads at the sandwiching station. These hoppers are fitted with stirrers to prevent settling and air entrapment. Each depositor head is servo-controlled and fitted with a positive shut-off nozzle that prevents dripping or stringing. The precise volume dispensed per cookie is monitored using feedback from a load cell mounted under a sampling tray, which collects data after every few hundred cycles for calibration. In parallel, the cookie halves exiting the oven are gently conveyed onto transfer belts that align them for filling. These belts operate in tandem with the sandwiching equipment, using position encoders to match the speed of each cookie half to the movement of the depositor heads. This ensures that each filling bead lands perfectly centered. After deposition, the top halves are placed automatically, as previously described, and each sandwich proceeds to the compression conveyor for final shaping. Cookies are now complete and enter a buffering conveyor that allows temporary accumulation without halting upstream processes. This buffering zone is essential for absorbing brief disruptions in the packaging line and ensures a continuous flow without stopping baking or filling operations. The buffering conveyor consists of overlapping belts with friction rollers that decouple belt movement, allowing cookies to compress into a queue without collision damage. From the buffer zone, cookies are metered into lanes that feed the flow wrapping system. Lanes are formed using guide rails and diverter gates controlled by proximity sensors. The speed and volume of flow into each wrapping lane are adjusted automatically based on downstream demand. This real-time responsiveness ensures that wrapped units are supplied to the cartoning stage without overloading or starving the system. Once wrapped and sealed, each pack passes through a final metal detection unit. This detector uses dual-frequency electromagnetic fields to identify the presence of any metallic contamination. The sensitivity is high enough to detect ferrous and non-ferrous particles as small as 0.8 millimeters. Packages that trigger the detector are automatically diverted into a lockable reject bin for further inspection, while clean packs continue toward cartoning and case packing. Feastables chocolate begins with bulk delivery of raw cacao beans. The beans arrive in large jute sacks and are poured into a vibrating hopper. The vibration sorts debris and dust from the beans. From there, a conveyor lifts the beans into a destining machine. This machine uses air jets and sieves to remove stones, metal fragments, and dense impurities. Next, the beans pass through an infrared or rotary drum roaster. The internal temperature is precisely controlled, typically between 120 degrees C and 150 degrees C. The roasting drum rotates continuously, ensuring even heat distribution. As the beans roast, moisture evaporates and flavor precursors begin to develop. The outer shells become brittle. Once roasted, the beans are fed into a winnower. This machine cracks the beans and separates the lightweight husks from the dense nibs using a combination of rollers, suction, and vibration. The result is a stream of clean, uniform cacao nibs. These nibs are conveyed to a pre-grinder. Inside, steel rollers or rotating discs crush the nibs, releasing cocoa butter and forming a thick paste called cocoa liquor. The texture shifts from gritty to smooth as the particles are reduced to below 100 microns. This liquor is held in heated tanks to maintain fluidity. A precise ratio of cocoa liquor, cocoa butter, sugar, and optional ingredients like sunflower lecithin or vanilla powder is then metered into a mixing vessel. For milk chocolate variants, milk powder is added. The mixer uses rotating paddles and scrapers to fold and blend the mixture. The dry and liquid phases integrate into a homogeneous, gritty paste. This mixture is then transferred to a refining system. Typically, it enters a 5-roll refiner. The paste moves through a series of steel rollers, each tighter than the last. The rollers spin at different speeds, shearing and compressing the particles. Particle size is reduced to 15 to 20 microns. This step gives the chocolate its smooth mouthfeel. After refining, the fine chocolate powder enters the conche. The conche is a heated trough with rotating blades. The blades knead and aerate the chocolate for hours, sometimes up to 24 hours. Frictional heat raises the temperature to 58 to 60 degrees. Acidity and volatile compounds evaporate. The texture becomes fluid and the flavor mellows. At the end of conching, the chocolate mass is pumped into holding tanks. These tanks are jacketed with hot water or oil to maintain a precise temperature and viscosity. The chocolate is now fully developed, but still needs tempering. The tempering process begins. In an automatic tempering machine, the chocolate flows through a series of heat exchangers. First, it is cooled rapidly to around 27 degrees Celsius. Then, it's gently reheated to approximately 31-32 degrees Celsius. This controlled crystallization ensures that only stable cocoa butter crystals, form 5, remain. The chocolate emerges with a glossy finish, a crisp snap, and resistance to bloom. Tempered chocolate is dispensed into polycarbonate molds using a depositor. Each mold moves along a belt under the depositor head. Pneumatic pumps release precise volumes of chocolate into each cavity. The molds then vibrate on oscillating plates to release air bubbles and level the chocolate surface. For bars with inclusions like crisped rice or quinoa, these dry ingredients are pre-weighed and dropped into the molds before or after deposition. A brief pass through a secondary vibration stage ensures even distribution. The filled molds enter a multi-zone cooling tunnel. The tunnel gradually lowers the temperature from 20 degrees Celsius to below 10 degrees Celsius over 15 to 20 minutes. Cold air circulates evenly around the molds. The chocolate solidifies and contracts, releasing cleanly from the mold walls. At the end of the cooling tunnel, a demolder inverts each mold and uses pneumatic fingers or vibration to eject the solid bars onto a conveyor. Bars with visual defects or broken corners are automatically rejected by a vision system. The flawless bars move toward the wrapping station. First, they pass under a metal detector. Any product triggering the sensor is rejected. Accepted bars proceed to flow wrapping. In the flow wrapper, film material is unwound from a large roll. Rollers and guides stretch and align the film. As the chocolate bar approaches, a photocell detects registration marks on the film. The bar is enveloped in the film and heat-sealed longitudinally along the bottom. End seals are formed using rotating crimpers that simultaneously cut and seal the package ends. Sealing jaws apply controlled heat and pressure to ensure airtight closure. Wrapped bars are transferred to a check weigher. Each bar is weighed at high speed. Overweight or underweight bars are rejected via a pneumatic pusher. Conforming bars continue on the line. Next, a robotic arm arranges the wrapped bars into a collating station. A programmable pick-and-place system grabs a fixed number of bars, usually 12 or 24, and loads them into a preformed carton or display box. The cartons are fed from a magazine and erected mechanically with glue applied by a precision nozzle. Filled cartons pass through a carton sealer. Top flaps are closed and sealed with hot melt adhesive. A roller press ensures adhesion. Barcodes and date codes are printed using an inkjet coder or laser etcher as the cartons move along. Cartons are grouped on a secondary conveyor and conveyed to a palletizing cell. Here, a robotic palletizer with suction cups or mechanical grippers stacks cartons in alternating patterns onto wooden or plastic pallets. Slip sheets may be inserted between layers to prevent shifting. Once a pallet is complete, it moves to a stretch wrapping station. A rotating arm wraps the pallet in clear stretch film from top to bottom. Tension is automatically adjusted based on load size and weight. The final wrapped pallet is conveyed to staging for outbound shipment. Throughout the process, programmable logic controllers, PLCs, synchronize timing, temperature, flow rate, and sensor feedback across the line. The entire system operates in a closed-loop, high-efficiency sequence. Raw cacao is transformed into a uniform, shelf-stable product through thermal processing, grinding, mixing, tempering, molding, wrapping, and palletizing. Each machine is tuned to maintain product consistency within tight tolerances. Distinctive mechanical features include the 5-roll refiners' progressively tighter gaps, the conch's continuous shearing and aeration, and the tempering unit's 3-zone thermal profile. These machines operate with minimal variation, ensuring texture, flavor, and finish are uniform across thousands of bars per hour. Production speeds vary by line configuration, but a high-capacity setup can process over 300 bars per minute. The synchronization between depositors, conveyors, coolers, and wrappers is maintained via servo motors and real-time monitoring systems. Cameras and load cells detect alignment, weight, and position at multiple checkpoints. Chocolate variants with mix-ins follow the same base process with additional ingredient hoppers. These hoppers dispense inclusions onto conveyor-fed molds with augers or vibratory feeders. Sensors confirm the inclusion amount by weight or volume before chocolate is deposited. For filled bars, a 2-stage depositor is used. The first depositor fills the mold cavity halfway with chocolate. The mold is vibrated and partially cooled. Then, a filling such as nut butter or caramel is injected by a piston depositor. A second chocolate layer is deposited over the filling, and the mold is vibrated again before entering the cooling tunnel. Temperature control is maintained at every stage. Heated pipes transfer chocolate between tanks and machines. Sensors constantly monitor chocolate viscosity, pump pressure, and flow rates. Any deviation triggers an automatic adjustment or line stop. All chocolate contact surfaces are made from stainless steel. CIP, clean-in-place systems, are integrated into tanks and pipes, allowing the entire system to be flushed with heated cleaning solutions and rinsed without disassembly. During production, a SCADA, supervisory control and data acquisition system, provides a real-time visual interface for operators. It displays machine status, fault alerts, production counts, and temperature trends. Cadbury Dairy Milk Chocolate begins with bulk raw materials delivered into the production facility: fresh liquid milk, granulated sugar, cocoa liquor, cocoa butter, and milk crumb. Each component is handled in temperature-controlled conditions and introduced into the system through automated silos and dosing feeders. The fresh milk is first converted into milk crumb, a defining ingredient in dairy milk's formulation. This process starts by pumping whole milk into a vacuum evaporator, where water is removed under low pressure. The concentrated milk is then combined with sugar in a heated blend tank. This mixture is transferred to rotating roller dryers. As the sweetened milk film spreads over the hot steel drums, it rapidly dries and forms a brittle, flaky layer. Scrapers detach the dried sheet, breaking it into coarse milk crumb. Milk crumb is conveyed pneumatically to storage silos, where it remains dry and ready for use in chocolate mixing. This form provides dairy milk with its unique, creamy texture and long shelf stability. Meanwhile, cocoa liquor and cocoa butter are stored separately in jacketed tanks, kept at a constant temperature to ensure flowability. The cocoa liquor, ground from roasted, winnowed cocoa nibs, is thick and rich. The cocoa butter, either pressed from liquor or sourced independently, is pale, fluid, and high in fat. Next, the primary mixing stage begins. Automated dosing systems weigh and release precise ratios of cocoa liquor, cocoa butter, milk crumb, and granulated sugar into a large horizontal mixer. This unit features dual counter-rotating shafts and side scrapers that continuously fold the ingredients. The mixture gradually develops from dry and gritty into a heavy, uniform chocolate dough. This dough is then fed into a 5-roll refiner. The refiner consists of 5 parallel steel rollers, each rotating at increasing speed. As the chocolate paste passes through each roller gap, particle size is reduced progressively, from hundreds of microns down to between 15 and 20 microns. The result is a dry, fine chocolate flake with a silky texture at the microscopic level. After refining, the chocolate flakes are transferred to the concha. The concha is a large, temperature-controlled trough equipped with heavy-duty rotor blades. The chocolate is kneaded continuously with friction-generating heat. Temperatures rise to around 55 degrees Celsius. This process can last from several hours to over a day, depending on the desired flavor development. Volatile acids are driven off, moisture is reduced, and cocoa solids are fully coated with fat, creating a smooth, aromatic chocolate base. Following conching, the chocolate mass is pumped through heated pipes into intermediate holding tanks. These tanks maintain the chocolate at a constant temperature to preserve its fluidity and prevent premature crystallization. Agitators inside the tanks ensure uniform consistency and prevent settling. From here, the chocolate undergoes tempering. An automatic tempering machine circulates the chocolate through a sequence of heat exchangers. First, the temperature is raised to fully melt all cocoa butter crystals. Then, the chocolate is cooled to about 27 degrees, prompting the formation of stable seed crystals, form phi. Finally, it is reheated slightly to around 31-32 degrees Celsius, dissolving unstable crystals, but preserving the desirable structure. This gives the final chocolate its signature gloss, snap, and resistance to fat bloom. Tempered chocolate flows into a depositor system. Polycarbonate molds pass beneath the depositor head on a continuous belt. Precision nozzles fill each mold cavity with a set volume of liquid chocolate. For filled variants, a stage depositor is used. A bottom chocolate layer is poured and cooled, followed by a filling injection, such as caramel or nougat, and topped with another chocolate layer. Molds then travel onto vibrating platforms, which shake out air bubbles and level the surface. The vibrating phase lasts just a few seconds, but is crucial for creating a smooth finish and ensuring complete mold fill. Next, the filled molds enter a multi-stage cooling tunnel. This enclosed chamber has progressive cooling zones, starting around 20 degrees Celsius and decreasing to below 10 degrees Celsius. The controlled descent in temperature allows the chocolate to solidify evenly and contract slightly, easing release from the molds. Cold air is an automated rejector gate. Perfect bars continue toward packaging. First, they pass through a metal detector which scans for ferrous and non-ferrous particles. Cleared bars enter the flow wrapping system. In the flow wrapper, a printed foil wrapper is unwound from a roll and cut to size. As the chocolate bar moves along the conveyor, it is enveloped in the wrapper. A heated crimp sealing mechanism closes the back seam and simultaneously cuts and seals both ends. The wrapping film is heat sensitive and printed with registration marks to align branding and ensure uniform presentation. Wrapped bars move along a conveyor to the check weigher. Each package is weighed at high speed using load cells. Any bar outside the preset weight tolerance is immediately rejected. Compliant bars continue to cartoning. Here, an automated carton erector forms cardboard display boxes. A robotic pick-and-place arm loads wrapped bars into the cartons, arranging them in fixed rows. Hot melt glue without crushing the cartons. Throughout the entire Cadbury dairy milk production process, every system is managed by a centralized PLC, programmable logic controller, network. These systems coordinate flow rates, temperature set points, and equipment timing. Sensors along each conveyor track product speed, mold position, and fill levels in real time. Data from all units feed into a SCADA, supervisory control, and data acquisition interface, allowing operators to monitor trends, alarms, and equipment health at a glance. Flow meters, load cells, thermocouples, and vision sensors ensure that the chocolate's physical and visual properties are maintained to exact standards. In multivariant production lines, switchovers between bar sizes or recipes are handled via modular machine components. Depositor heads, mold formats, and wrapping film rolls can be exchanged with minimal downtime. Servo motors and memory-driven positioning systems recalibrate machinery for different dimensions automatically. For filled bars or multi-layer variants, rotary depositors inject fillings such as fudge, caramel, or fruit puree between chocolate layers. These fillings are stored in separate heated tanks and dispensed through jacketed pipes to maintain flow without separation. Every chocolate contact surface is stainless steel, designed for CIP, clean-in-place systems. After production cycles, cleaning valves open and circulate alkaline detergents, followed by a water rinse to sanitize the interior of tanks, pipes, and mixers. The entire Cadbury dairy milk process, from fresh milk to molded bar, operates in a closed, highly automated loop. Thermal stages, particle size reduction, emulsification, crystallization, and molding are orchestrated to maintain the exact texture, sweetness, and melt profile that define the finished product. From the rolling dryers that turn milk into crumb, to the 5-roll refiners that shear cocoa particles, to the vibrating mold beds and precision wrapping crimpers, each machine plays a role in transforming bulk ingredients into a consistent, shelf-ready chocolate bar. High-capacity lines can produce thousands of bars per hour, with conveyors spanning hundreds of meters across multiple zones. The process flow is linear, but segmented into temperature, flow, and pressure-controlled modules, each ensuring precise control over the material's transformation from liquid to solid, from raw to refined. Mars chocolate bars begin with the precise handling of their core components: sugar, cocoa mass, cocoa butter, skimmed milk powder, glucose syrup, lactose, and vegetable fats. Each ingredient is delivered in bulk. Liquids stored in jacketed stainless steel tanks, powders and solids transferred through enclosed pneumatic conveyors into weight-controlled silos. The process initiates with the creation of the chocolate base. Cocoa liquor, also known as cocoa mass, is pumped from heated storage tanks into a large jacketed mixer. Along with it, metered quantities of cocoa butter, sugar, and milk powders are added. This mixture is stirred with high-torque paddles under heat to form a semi-dry paste. The mixing cycle is tightly controlled to ensure homogeneity of particle distribution before size reduction. The paste moves next into a 5-roll refiner. This machine consists of 5 steel rollers aligned horizontally, each rotating at progressively higher speeds. The chocolate mass is compressed and spread across each roller in sequence. As it passes through the narrowing gaps, particle size is reduced to between 15 to 20 microns, creating a fine, uniform flake that feels smooth on the tongue. These flakes are transferred to conchas, elongated troughs equipped with rotating agitators. The friction between the rotating arms and the flakes generates heat, bringing the chocolate to around 55 degrees. This step is vital for flavor development and smooth texture. During conching, volatile acids and moisture evaporate, and cocoa solids are thoroughly coated with fat. The result is a free-flowing, aromatic chocolate liquid. Tempered storage tanks receive the conched chocolate. These tanks are equipped with agitation blades and heat exchangers, maintaining a stable temperature to keep the chocolate fluid. From here, it is pumped into tempering units, where it undergoes controlled cooling and reheating. The goal is to crystallize only the stable form V cocoa butter crystals. Tempering involves 3 precise temperature stages. First heating the chocolate to about 45 degrees Celsius, then cooling it to 27 degrees Celsius to initiate crystal formation, and finally reheating to around 31 degrees Celsius. This thermal profile ensures the finished chocolate has a shiny appearance, a sharp snap, and resistance to blooming during storage. While the chocolate is being prepared, the nougat base is made separately. A pre-blend of sugar, glucose syrup, egg white powder, milk powder, and salt is mixed in a high-speed planetary mixer. The mixture is heated to a specific temperature, typically around 120 degrees Celsius, and whipped under pressure. As air is incorporated, the texture becomes light and spongy. The output is a warm, aerated nougat mass, which is discharged onto a belt in a continuous sheet. This nougat sheet moves through a calibrating roller system that flattens it to the target thickness, typically 12 to 16 millimeters. The sheet passes under an infrared scanner to check its uniformity. Next, it enters a chilling tunnel, where cold air reduces the temperature to stabilize its structure for the next layer. Once chilled, the nougat layer receives a caramel topping. Caramel is prepared in a separate, continuous cooker. A mixture of glucose syrup, sweetened condensed milk, and vegetable fat is cooked under vacuum to around 118 degrees Celsius. It is then cooled slightly and deposited onto the nougat sheet through a wide slot applicator. The caramel spreads across the surface in a uniform layer, with its viscosity controlled by temperature. The combined nougat caramel sheet passes through another set of rollers to achieve precise height. It then enters a second cooling tunnel, where the caramel layer is stabilized and slightly hardened. After cooling, the multi-layer slab is cut into individual bar-sized fingers using a guillotine cutter. First, the slab is cut laterally into long ribbons. Then, rotary knives or ultrasonic blades slice each ribbon perpendicularly into pieces of exact length. The blades operate at high speed, synchronized with the belt to avoid distortion or smearing. These cut fingers are spaced evenly and conveyed toward the enrobing station. Enrobing is the process where each bar is fully coated in liquid tempered chocolate. The enrober has a curtain of flowing chocolate that falls from a weir. As the bars pass beneath the curtain, chocolate coats the top and sides. a bottoming station simultaneously floods the base with chocolate. Excess chocolate is removed by an air knife that blows a controlled jet of air, creating the classic ridge surface on top of the bar. Enrobed bars immediately enter a cooling tunnel. This tunnel consists of several cooling zones, gradually reducing the temperature from ambient to around 8 to 10 degrees Celsius over 5 to 7 minutes. Chilled air circulates from multiple directions to ensure even setting of the chocolate coating. Exiting the cooling tunnel, the now solid Mars bars pass through a metal detector for contamination control. Each bar is scanned for ferrous and non-ferrous metal fragments. Bars that pass inspection proceed directly to wrapping. The wrapping system is a high-speed flow wrapper. Printed film is unwound and cut to size by a rotary knife. As each bar approaches, the film is formed around it and sealed lengthwise along the bottom with a heat bar. Crimpers then seal both ends and cut between each unit, forming an airtight package. The position of the branding and barcode on each wrapper is controlled by registration marks and optical sensors. Each wrapped bar moves to a check weigher that confirms product weight. Bars falling outside the set, tolerants are rejected via a pneumatic arm. Acceptable bars move onward to collation and cartoning. A collating conveyor arranges the bars into rows and stacks them in groups. Robotic pick-and-place arms, equipped with vacuum heads, lift the grouped bars and insert them into pre-formed cartons. The cartons are formed from flat blanks by a mechanical erector, which folds and seals the base flaps with hot melt glue. Filled cartons pass through a closure unit where top flaps are folded and glued shut. The cartons then pass under an inkjet or laser coder, which prints best before dates, production times, and batch codes on each unit. For bulk distribution, cartons are transferred to an automated palletizer. A robotic arm places the cartons in pre-programmed patterns on a standard pallet. Slip sheets are inserted between layers as needed. Once the pallet is complete, it is stretch wrapped by a rotating arm that applies plastic film from top to bottom under tension. Each segment of the Mars bar production line is governed by PLCs, programmable logic controllers, which synchronize all motor functions, flow rates, temperatures, and timing sequences. Sensors placed throughout the system continuously feed data to a SCADA, supervisory control, and data acquisition interface. Operators monitor real-time performance, trend data, and alarms from centralized control panels. Temperature sensors in the caramel cooker, nougat mixer, and chocolate tempera maintain thermal precision within plus a 0.5 degree Celsius. Load cells in dosing hoppers regulate ingredient input by mass. Viscosity sensors in chocolate tanks and caramel pipelines provide feedback to flow controllers and ensure consistency during deposition. Mars bar production lines are modular and capable of format changes. Swappable depositor heads, adjustable belt guides, and programmable cutter settings allow the system to handle different bar sizes, weights, or recipe variants. The enrobing line can switch chocolate types, milk, dark, or white, by flushing the system with CIP, clean in place, protocols. CIP systems are built into tanks, pipes, and enrobers. These automated cleaning cycles use heated caustic solutions followed by sterile water rinses. The process is run between product types or during shift changes. Filled bar variants, such as those with peanut butter, cookie dough, or layered textures, use dual-stage deposition. After the nougat base is laid down, a second depositor applies a defined filling stripe. A heated spreader may be used to smooth viscous fillings. The caramel and chocolate enrobing proceed normally after this stage. Production lines for Mars bars typically operate at speeds up to 300 bars per minute, depending on bar size and configuration. The entire process, from raw ingredients to palletized cartons, takes place over a footprint of several hundred meters of continuous machinery, arranged in a linear but interlinked layout. Distinctive mechanical features include the dual cooling tunnels for nougat and caramel stabilization, the high-pressure air knife for chocolate surface texturing, and the inline ultrasonic blade system that cuts without deformation. Every component in the process is engineered for consistency. Chocolate viscosity is regulated through controlled fat content and shear mixing. Caramel texture is tuned by managing cooking time and water activity. Nougat aeration is monitored with pressure transducers and density meters in real time. The Mars chocolate bar emerges from this high-precision mechanical sequence as a fully formed, enrobed, wrapped, and coated product, engineered for consistency in texture, layering, and appearance. Every detail, from the shear of the 5-roll refiner to the calibration of caramel applicators, contributes to the uniformity of each bar produced. The process begins with the reception of raw cacao beans. These arrive in large burlap sacks, which are automatically tipped into a stainless steel hopper. The hopper feeds a vibratory conveyor, shaking the beans in a controlled rhythm to remove debris and small stones. As the beans travel, high-powered magnets and air jets eliminate metallic fragments and lighter contaminants. Once cleaned, the beans move into the roasting chamber. This is a horizontal, drum-style roaster with precise temperature zones along its length. The beans are roasted between 120 degrees Celsius and 150 degrees Celsius for 30 to 45 minutes, depending on origin and moisture content. Inside the rotating drum, baffles lift and drop the beans repeatedly to ensure even exposure to heat. The surface crackles as volatile acids are driven off, and the aroma intensifies. Roasting profiles are strictly controlled using infrared sensors and thermal probes. After roasting, the beans exit into a rapid cooling system, a double-jacketed air cooling tunnel that quickly brings the temperature down to prevent over-roasting. As the beans cool, they're conveyed to the winnowing station. Here, a precision cracking roller gently fractures the outer shells. The mixture then passes through an ascending air column. Shells, being lighter, are blown upward and extracted into a cyclone separator. The heavier nibs fall downward, separated cleanly. The nibs are then routed into the liquor grinding system. This involves a 2-stage reduction process. First, a coarse grinder reduces the nibs into a paste-like mass using granite rollers. This mass, still gritty, feeds into a 5-roll refiner. The rolls are made from hardened steel and arranged in descending gap widths. The rollers spin at increasing speeds to shear the particles down to 20 microns. During this stage, the paste becomes smooth and glossy, now known as chocolate liquor. From the refiner, the liquor is pumped into a conching machine. This is a long, horizontal tank with heavy granite paddles. The paddles rotate slowly but forcefully, kneading the liquor for up to 72 hours. During this process, frictional heat raises the temperature to 50-60 degrees Celsius. This drives off unwanted volatiles and enhances texture. As it churns, the chocolate undergoes subtle flavor transformation and becomes fluid, velvety, and aerated. At this stage, additional ingredients are introduced through precision feeders. Sugar is added via a sealed screw conveyor that meters crystalline particles in carefully measured doses. Milk powder, if producing milk chocolate, is pre-blended with a small portion of cocoa butter before being added. The mix is tested repeatedly with inline viscometers and particle size analyzers to ensure consistency. Next, the chocolate moves into the tempering system. This consists of 3 stainless steel heat exchangers that rapidly cycle the chocolate through defined temperature curves. The liquid chocolate is cooled from 45 degrees Celsius down to around 27 degrees Celsius and then reheated to 31 or 32 degrees Celsius. This carefully controlled crystallization process encourages the formation of stable cocoa butter crystals, Form 5, which gives the final chocolate a glossy finish and crisp snap. Once tempered, the chocolate is ready for molding. It flows into automated depositor heads mounted above polycarbonate molds. Each head features multiple precision nozzles controlled by servo motors. The nozzles deposit exact volumes of chocolate into the cavities, synchronized with the moving mold belt below. Vibration tables mounted beneath the molds shake rapidly, eliminating trapped air and evening out the surface. The molds enter a cooling tunnel, a refrigerated corridor where temperature and humidity are tightly regulated. Inside, a chilled airflow passes over the molds for 10 to 15 minutes, bringing the chocolate down to 8-10 degrees Celsius. This solidifies the product and locks in the tempered structure. Once cooled, the molds are inverted and gently flexed by mechanical arms to release the solid chocolates. They drop onto a food-grade conveyor belt, which directs them to the decorating and enrobing section. Here, high-speed cameras inspect the chocolates for surface defects, rejecting any that are misformed or marred. If filled or layered chocolates are being produced, the process diverges earlier. In that variation, the molds receive only a thin chocolate shell in the first deposit. These shells are then cooled, filled with praline, ganache, or fruit paste through precision piston fillers, and then sealed with a final layer of tempered chocolate before full cooling. Back on the main line, the finished solid chocolates enter the enrobing tunnel if they require coatings. This consists of a continuously flowing curtain of tempered chocolate falling from a weir system. The chocolates pass beneath the curtain on a wire mesh belt, receiving a uniform coating. Excess chocolate is blown off the bottom by air knives positioned beneath the belt. After enrobing, the products move through another cooling tunnel. This secondary tunnel is slightly longer and maintains cooler airflow at 6-8 degrees Celsius to ensure the coating sets with a uniform sheen. Inside, multiple temperature zones gradually reduce the product temperature to avoid bloom or condensation. Next is the decorating phase. This station uses robotic arms fitted with ultra-fine nozzles and stampers. The arms are guided by a 3D vision system to identify the orientation of each piece. Depending on the product, they may apply fine chocolate stripes, edible gold dust, cocoa powder, or even embossed logos using heat press stamping heads. Some lines include a nut topping mechanism that drops single pistachios or almonds onto the still soft chocolate surface with pneumatic precision. From here, the chocolates move to the buffering conveyor. This is a serpentine belt that temporarily holds products in case downstream machines slow down or halt. It prevents product collisions and maintains production flow without pause. Once flow resumes, the chocolates proceed to the wrapping line. The wrapping process begins with a high-speed feeder system. Chocolates arrive in single file along a narrow conveyor aligned by adjustable guide rails. As they approach the wrapping unit, an optical sensor scans each piece to verify orientation and spacing. A star wheel indexing system captures each chocolate in a rotating pocket, ensuring it enters the wrapping machine at precisely timed intervals. For individually wrapped pieces, the wrapping style depends on the product type, either fold wrap, twist wrap, or flow wrap. Fold wrap is used for rectangular or square chocolates. A continuous roll of foil, ynens, often metallized polypropylene or laminated aluminum, feeds into a cutting station. A servo-driven knife slices the foil into perfectly sized sheets. A vacuum picker transfers each sheet onto a wrapping plate where a chocolate rests. Pneumatic folders quickly tuck each edge of the foil around the chocolate with clean, creased folds. And heated plates press the final seam to ensure adhesion without adhesives. In twist wrapping, used for rounded or pillow-shaped pieces, the chocolates are dropped into film pockets on a rotating turret. As they spin, two heated jaws grip the ends of the film and twist them in opposite directions in a single, fluid motion. The result is a tight double twist at both ends with no glue, secured purely by friction and film memory. Flow wrapping is reserved for bars or longer chocolates. Chocolates move onto a horizontal flow wrapper in perfect rows. A forming box folds a continuous film web into a U-shape around the moving product stream. Longitudinal sealing wheels fuse the film along the bottom seam using heat and pressure. Rotary end sealers then crimp and cut between each chocolate in one continuous motion. The result? A tight, seamless pillow pack with serrated edges. Once wrapped, products pass under a metal detector integrated with an automatic reject arm. Any contamination triggers an immediate air jet that diverts the product off the main line without interrupting flow. Approved chocolates continue to the labeling and grouping section. For chocolates requiring labels or tamper-evident seals, a label applicator aligns pressure-sensitive labels onto the wrapper surface with micron-level accuracy. For sealed tags or holograms, a rotary arm applies the label with static discharge to eliminate air pockets. High-speed vision systems verify placement and orientation, rejecting any misaligned units. Next, the wrapped chocolates are grouped into sets for final boxing. This is handled by a Delta robot pick-and-place system. Using 3 arms mounted on a gantry and guided by overhead cameras, the robots lift chocolates from the conveyor and deposit them into plastic or cardboard trays. The trays are held on index pallets that move step by step beneath the robot's reach. Depending on the SKU, arrangements may be linear rows, nested pyramids, or offset diagonals. If the product is a boxed chocolate assortment, the process diverges again. Assorted trays begin with an injection molded plastic insert, which is automatically placed into a folding carton. Chocolates are sorted by type and delivered to multi-head pickers. Each picker arm uses vacuum suction or soft rubber grippers to lift specific chocolates and place them in precise tray compartments. The sequence is synchronized to ensure correct assortment patterns. No duplicates, no gaps. Once loaded, these trays move to the lid application station. A folding carton blank is fed into a forming mandrel, where pneumatic fingers erect and glue the box around the insert. A transparent film or foil seal is sometimes heat applied across the top, shrinking snugly into place. Then, a decorative lid is pressed on with a spring-loaded arm to achieve a flush seal. If a rigid luxury box is used, an entirely separate line assembles it. Die-cut cardboard is laminated with printed paper and hot-pressed into box forms. Magnets or ribbon closures are inserted automatically by articulated tools. The finished boxes are then transferred via robotic arm to receive their filled trays. From here, final boxing and case packing begins. Chocolates, now individually wrapped or boxed, arrive on a wide accumulation belt. Automatic collators organize them into bundles of 6, 12, or more, depending on shipping unit configuration. These bundles are pushed into carton erectors where flat corrugated blanks are folded around them, glued and pressed shut. Some lines use wraparound case packers. In this method, the grouped products are held stationary as a blank corrugated sheet is wrapped around all sides. Mechanical arms fold the flaps, apply hot melt glue, and compress the bundle into a sealed shipping case. These cases exit onto a short conveyor where industrial inkjet printers mark each side with batch numbers, timestamps, and QR trace codes. The case is then moved to the palletizing zone. Here, a robotic arm with a vacuum plate or gripper head arranges cases onto pallets. Each layer follows a programmed stacking pattern, alternating orientations for stability. After each layer, a slip sheet may be inserted by an automated feeder. Once the full stack is complete, often up to 2 meters high, the pallet is conveyed to a stretch wrapping machine. The stretch wrapper features a rotating turntable and a film carriage that moves vertically. As the table spins, the carriage stretches and applies multiple layers of plastic film under tension. This secures the load tightly and protects against moisture and dust. Some systems include a top sheet applicator that lays a waterproof plastic sheet across the top before wrapping. Finally, the fully wrapped pallets are conveyed through a weight check station and scanned by a vision system for final verification. They are now ready for shipment. A precisely manufactured, delicately handled series of chocolates transformed through over 24 distinct mechanical stages from raw bean to boxed luxury. For filled and layered chocolates, the factory employs a specialized multi-stage molding line. This system operates on a closed-loop conveyor that continuously cycles polycarbonate molds through a sequence of precisely timed stations. Each mold contains multiple cavities, and every station in the circuit performs a distinct action in the assembly of complex, filled products. The process begins with the shell-forming station. A depositor head releases a measured volume of tempered chocolate into each mold cavity. Immediately, the molds move to a tilting station, where they are flipped and vibrated simultaneously. Centrifugal force causes the chocolate to coat the sides and bottom of each cavity evenly, leaving a hollow center. Any excess chocolate flows out and is reclaimed. After inversion, the molds pass under a chilled airflow, rapidly setting the shell. Once the shell is solidified, the molds continue to the filling station. This unit features servo-controlled piston depositors mounted above each cavity. The fillings are stored in heated hoppers to maintain fluid consistency. These can include hazelnut praline, fruit compotes, flavored ganache, caramel, or nut pastes, each delivered through dedicated nozzles. The depositors lower and inject precise quantities into each chocolate shell without disturbing the walls. Viscosity is controlled via inline heating coils wrapped around the filler lines. Every filling passes through mass flow meters to ensure consistency across thousands of units. Between each product type, CIP, clean-in-place systems, purge the lines with high-pressure heated water, followed by compressed air to eliminate cross-contamination. Next, the filled molds pass through a brief cooling tunnel. This lowers the filling temperature just enough to create a thin surface skin, ensuring it doesn't mix with the final chocolate seal. At the cap sealing station, another depositor head applies a top layer of tempered chocolate, sealing each cavity shut. This chocolate is deposited with high precision, covering the filling completely and fusing to the shell edges. Vibration tables beneath the molds remove trapped air and ensure a flush finish. The molds then enter a long cooling tunnel, typically spanning over 10 meters. This tunnel contains multiple chilled zones that gradually reduce product temperature from 30 degrees Celsius to under 10 degrees Celsius. The slow, staged cooling prevents shrinkage or cracking and allows the chocolate to fully contract away from the mold walls. Once cooled, the chocolates are ejected mechanically. Pneumatic plungers behind each mold cavity gently push the finished pieces downward onto a soft conveyor. These filled chocolates proceed to surface treatment. For layered chocolates, a similar system is used with key variations. After the first shell is deposited and cooled, a layer of inclusions, such as crushed nuts, cookie pieces, or fruit granules, is sprinkled into the mold by an oscillating vibratory feeder. A light pressure roller presses the inclusions into place. Then, a layer of filling is added, followed by a capping layer of chocolate. This creates a tri-layered cross-section when cut or bitten. Aerated chocolates follow a different method entirely. Here, the chocolate is first fed into a pressurized vacuum chamber. Under controlled vacuum, nitrogen gas is injected into the chocolate stream through a sparger, a perforated titanium rod. The gas forms microbubbles, which are then locked in by suddenly returning the chamber to atmospheric pressure. The now aerated chocolate has a mousse-like texture, yet remains stable once cooled. This aerated mixture is deposited into molds using modified volumetric heads that prevent bubble collapse. Because of the internal gas structure, aerated chocolates are cooled more gently to avoid rapid contraction. They pass through a specialized tunnel with fine-tuned temperature gradients that stabilize the internal structure. Some advanced variations include dual flavor split molds. These use two separate depositors operating in tandem, each filling half of the mold cavity with a different chocolate, such as milk and white or dark and ruby. A precision divider plate inside the nozzle ensures a clean, vertical split. The chocolates are deposited simultaneously, then vibrated and cooled, just like single origin types. Another variant involves inclusions in the chocolate itself. Before deposition, the base chocolate is mixed with particulate ingredients in a jacketed mixing bowl. These include puffed rice, freeze-dried fruit bits, chopped nuts, or biscuit crumbs. Agitators inside the bowl maintain even suspension. A positive displacement pump pushes the mixture through a large bore pipe to prevent clogging. Depositor heads with wider nozzles are used to handle the textured mass. For decorative layering, some lines use transfer film technology. A thin acetate film, printed with edible cocoa butter designs, is cut into sheets and placed on the bottom of each mold before chocolate is deposited. When the chocolate sets, the design transfers from the film onto the chocolate surface, creating intricate visual patterns. After cooling, the film is peeled away, leaving behind a vivid imprint. In other cases, chocolate pieces are stamped with embossed patterns or logos. After demolding, the chocolates move under a stamping head fitted with a heated metal die. The die is pressed lightly onto each piece, embossing it with a brand mark, pattern, or crest. The metal stamp is kept at 32 degrees Celsius, just warm enough to soften the surface without damaging structure. At this point, finished chocolates, whether filled, layered, aerated, or decorated, are directed toward the enrobing and topping station, if required. Some filled pieces receive an extra chocolate shell by passing through the enrobing curtain. Toppings such as sea salt flakes, crushed pistachios, or cocoa nibs are dispensed through multi-channel feeders synchronized with the belt speed. Each topping module includes a vibration sieve that controls granule size and drop rate. Sensors monitor belt occupancy to ensure no topping lands between products, minimizing waste. A gentle pressing roller may follow to embed toppings into the soft coating before cooling. Some premium chocolates are dusted with edible luster dusts or shimmer coatings. These powders are dispensed in an ultra-fine mist using electrostatic sprayers. The particles are positively charged as they exit the nozzle, adhering uniformly to the negatively charged chocolate surfaces. This creates a metallic or pearlescent finish with minimal overspray. For chocolates that require a hard shell glaze, a final step involves a rotating drum polisher. Chocolates are fed into the drum, which tumbles them gently while applying a thin mist of food-grade shellac or gum arabic. Internal warm air jets dry the glaze instantly, leaving a glossy, protective surface. Before reaching packaging, all finished chocolates pass through a multi-stage inspection tunnel. This includes laser-based shape detection, surface color analysis, and infrared temperature scanning. Products outside tolerance limits are ejected into designated bins. The final stage begins at the primary packaging line, where individual chocolates are grouped, positioned, and inserted into final, retail-ready formats. This step varies depending on the packaging style: rigid boxes, folding cartons, sleeve wraps, trays, tins, or multi-compartment assortments. Each format requires a dedicated configuration of pick-and-place systems, folder gluers, and sealing units. For rigid box assortments, chocolates arrive on an indexed belt and are picked by high-speed Delta robots equipped with vacuum suction heads. These robots place the chocolates into thermoformed plastic inserts, which are held stationary within open-bottomed rigid boxes. The inserts have precisely molded cavities matched to the contour of each chocolate piece. The robot arms adjust their speed and angle using dynamic feedback from overhead 3D scanners to avoid any misalignment. Once all cavities are filled, the boxes proceed to a film sealing station. Here, a roll of transparent BOP film is unwound, cut into sheets, and laid across the surface of the tray. A heated sealing plate presses the film into place, fusing it along the box edges to create a tamper-evident, airtight seal. The temperature of the sealing head is closely monitored by embedded thermocouples to maintain optimal adhesion without distorting the tray. For folding cartons, a different approach is used. Flat carton blanks, pre-printed and die-cut, are fed from a magazine stack into a carton erector. Mechanical arms fold the blank along pre-scored lines and apply hot melt glue in strategic points using precision nozzles. The forming mandrel compresses the carton into shape as it moves along the conveyor. Simultaneously, chocolates are grouped upstream by a collator belt, which aligns them into patterns matching the carton's internal layout. A pneumatic pusher slides each group into the open cartons as they move past. Once filled, the top flaps are folded and glued shut in a continuous motion. Some cartons are sealed with ultrasonic bonding, especially when glue-free closures are preferred. Specialty packaging formats, like sleeve wrap trays, begin with a plastic or cardboard tray filled with chocolates using robotic placers. A printed sleeve, flat and folded, is then placed over the tray. A servo-controlled banding unit wraps the sleeve snugly and applies a heat pulse to seal the overlap. These sleeves often include die-cut windows or embossing, requiring precise alignment during application. For metal tins or embossed boxes, an overhead conveyor delivers empty tins into position beneath the filling heads. Chocolates are stacked by robotic arms, using multi-head grippers that rotate to fit varied geometries. Once filled, the tins are lidded by a lid placement mechanism equipped with pneumatic actuators. The lid is pressed into place with a calibrated force to ensure a snug fit without warping the metal structure. In premium lines, inserts and accessories are added next. These include product guides, tasting menus, or promotional leaflets. A sheet feeder places the inserts into each box before final closure. In some configurations, a robotic arm adds a protective paper layer or a foil cover between the chocolates and the lid. When ribbon closures are required, a secondary robot wraps and ties the ribbons automatically using twin spindle tensioners and soft grippers. After primary packaging, products move into the overwrapping unit, especially for premium and seasonal items. A continuous film roll feeds through a forming collar to enclose each box. A fin sealer applies pressure and heat along the bottom seam, while side sealers tuck and seal the ends into neat folds. A cooling plate downstream sets the film structure immediately after sealing. Optional tear strips or easy open tabs are applied at this stage. These are pre-cut film sections with embedded threads or adhesives that allow consumers to open the product without tools. A precision applicator adds them just before the film is sealed, embedding them into the plastic without disturbing box integrity. Next is batch labeling and coding. An inkjet printer or laser etcher marks each box with its batch number, manufacturing date, expiration date, and unique identifier. For export products, a vision verification system checks every printed code in real time and compares it against the product database. Any mismatch causes an automatic ejection by a pneumatic diverter. Then, boxes enter the case packing line. A robotic case packer arranges the boxed units into shipping cartons according to a pre-programmed pattern. Each case is assembled from flat blanks in an automatic erector. Once filled, the case is sealed using a high-speed tape applicator or hot melt glue system. The type of seal depends on the distribution channel and climate conditions expected during transit. Some boxes are stacked vertically, while others lie flat, depending on product fragility and presentation. If protective dunnage or air cushions are required, an integrated dispenser adds these into the case before sealing. Completed cases are printed with destination codes and passed through a check weigher, which confirms that each box is within expected weight tolerances. At the end of the line, full cases are transferred to the palletizing system. A robotic palletizer uses a vacuum plate or mechanical gripper to stack the cases onto pallets in a staggered pattern. The stacking sequence is designed for maximum load stability. Between layers, corrugated slip sheets are automatically inserted from a magazine. Once the pallet reaches the target height, typically 1.8 to 2 meters, it is conveyed to a stretch wrapping machine. The turntable rotates the pallet while a film carriage moves vertically, wrapping it in multiple layers of stretch film. Tension sensors ensure that the film applies consistent pressure without crushing the product. For export pallets, a top sheet dispenser adds a final moisture barrier before wrapping is completed. The final wrapped pallet moves to the finished goods staging area. Here, each pallet passes through a scanning tunnel that records its dimensions, weight, and barcode data into the warehouse management system. Automated guided vehicles, AGVs, retrieve the pallets and deliver them to temperature-controlled storage areas where ambient humidity and temperature are monitored continuously. In some specialized lines, climate conditioning is introduced post-packaging. Products enter a controlled chamber that simulates various storage conditions. For instance, rapid temperature cycling from 10 degrees Celsius to 30 degrees Celsius to ensure product stability. Chocolates are held in this chamber for several hours before release to shipping to verify that they maintain integrity under stress. Before release, a final quality sampling system selects random units from each production batch. These samples are conveyed to a physical and sensory testing station, where robotic arms manipulate the products through breakage resistance tests, surface gloss readings via reflectometers, and cross-sectional scanning via laser slicers. The internal structure is analyzed for air pockets, alignment of layers, and crystallization consistency. Wheat flour is first delivered into large stainless steel silos, where it is aerated and sifted to remove any foreign carbonate and sodium carbonate are added. These alkaline agents raise the pH of the dough and produce the distinctive yellow color and firm, springy texture characteristic of cup noodles. The mixing chamber is equipped with twin shafts fitted with spiral paddles. These rotate in opposite directions, kneading the flour and water into a coarse dough. After a preset mixing time, the dough exits through a discharge chute and drops onto a sheeting conveyor. A pair of compression rollers press the dough into a wide, flat sheet of uniform thickness. The dough sheet then moves through a series of calibrated rolling stations. Each set of rollers reduces the thickness incrementally. Final gauge rollers press the sheet to a precise thickness, usually around 1 mm, before it enters the slitting unit. Here, rotary cutting wheels slice the sheet into long continuous strands. The blades rotate in exact synchrony with the moving dough, ensuring even noodle width and preventing tearing or overlap. The cut strands are separated by a vibrating spreader and immediately fed into a wave former. This mechanism applies a rhythmic up and down motion as the noodles pass over metal rods. The result is the iconic wavy noodle shape. The wave pattern is fixed into the strands by partially steaming them immediately after shaping. The noodles then enter a vertical steam chamber. Superheated steam, delivered through multiple nozzles, cooks the noodles for a brief but precise interval. The starches gelatinize and the surface becomes slightly sticky. This step fixes the texture while keeping the strands pliable. Upon exiting the steam chamber, the noodles are portioned. A wire cutter slices the strands into fixed lengths, which are gathered into bundles by rotary collectors. Each bundle is compressed slightly to form a compact cake. These cakes are positioned over pre-formed polystyrene foam cups on a conveyor system. Using a synchronized pick-and-place system, the noodle cakes are inserted into the cups from above. The cups themselves are formed earlier in the process using vacuum thermoforming machines. Polystyrene sheets are heated and drawn into mold cavities using vacuum suction. After forming, the cups are trimmed, stacked, and fed automatically to the noodle filling station. Once the noodle cake is placed into the cup, it proceeds to the dehydration stage. Unlike many instant noodles that are fried flat, cup noodles use a unique upside-down flash frying method. The filled cups are inverted and loaded onto a wire mesh conveyor belt that carries them through a continuous oil fryer. The oil, typically palm oil or a blend of vegetable oils, is maintained at a stable high temperature, usually between 140 degrees Celsius and 160 degrees Celsius. As the cups travel upside down through the fryer, the noodles are rapidly fried. Moisture evaporates from the strands, creating a porous, dehydrated structure that can be rehydrated quickly with hot water. The upside-down orientation ensures that the noodle cake maintains its shape and settles evenly inside the cup. Frying time is tightly controlled to prevent overcooking or excessive oil absorption. After frying through an inclined cooling tunnel, high-speed fans blow filtered ambient air over the hot cups to bring them to a stable handling temperature. Sensors monitor the internal temperature of the noodles to ensure uniform cooling before the next stage. Flavoring ingredients are added next. A separate filling system dispenses dried soup base and dehydrated vegetables or meats into each cup. The powder and inclusions, such as corn, peas, green onion, shrimp, or meat bits, are pre-blended in large hoppers. These are vibrated to prevent clumping and ensure free flow. As each cup passes underneath a dosing unit, precise quantities of the flavor mix and inclusions are released. Auger fillers handle the powder, while rotary cups or belt feeders portion the solid pieces. Lidding is the next step. A continuous roll of pre-printed aluminum foil is fed through a cutting die and sealing station. The foil is heat sealed onto the lip of each cup using a combination of pressure and temperature. The seal must be strong enough to prevent contamination, but easy to peel by hand. A vacuum system removes any air trapped between the noodle surface and the foil lid prior to sealing, reducing oxygen exposure and extending shelf life. Lidded cups proceed to the shrink sleeve labeling unit. A plastic film sleeve is positioned over each cup and then passed through a steam tunnel. The heat causes the sleeve to contract tightly around the cup, conforming to its shape. This sleeve contains branding, nutritional information, and preparation instructions. The orientation is adjusted using optical sensors to ensure perfect alignment with the cup's front face. After labeling, the cups are inkjet coated with production data, including date codes and batch numbers. A vision inspection system verifies code legibility and checks for misaligned labels or incomplete seals. Any defective cups are rejected automatically onto a side conveyor for rework or disposal. The finished, sealed, and labeled cups then enter the secondary packaging area. Depending on the distribution format, cups are grouped into packs of 6, 12, or 24 using a mechanical collator. These are pushed into pre-erected cardboard cartons supplied by a case-forming machine. Hot melt adhesive is applied to the flaps using spray nozzles, and the boxes are pressed shut by compression rollers. Each sealed carton passes over a check weigher to confirm correct content mass. Barcodes and product identifiers are applied using print and apply labeling machines. Cameras scan the labels to verify print quality and correct placement. The cartons are then transferred to the palletizing station. Robotic palletizers equipped with vacuum grippers or pneumatic pads stack the boxes onto wooden pallets in alternating layer patterns. Each layer is indexed and leveled using precision edge guides. Once a pallet reaches its designated height, it moves to the stretch wrapping station. Here, plastic film is wrapped around the pallet while it rotates on a turntable. Tension control and overlap percentage are adjusted dynamically based on pallet shape and weight. The wrapped pallets are labeled with a logistics ID, shipping docks, or warehouse storage zones. In parallel, all ingredients used in cup noodles, flour, salts, oils, seasonings, and dried vegetables are stored in bulk tanks and silos, filtered and UV sterilized before use. Oil for frying is circulated through a closed-loop filtration system that removes particulates and maintains clarity. Spent oil is drained and replaced after a set number of frying cycles, tracked by production batch logs. Quality control checkpoints exist at every stage. During dough mixing, operators monitor water absorption and dough elasticity using resistance sensors and torque readings. Sheet thickness is verified with laser micrometers before slitting. The width and wave depth of the cut noodles are measured optically in real time. Caramelization level and texture of the fried noodles are sampled from each batch and tested for rehydration time and oil content. Soup base and seasoning powders are blended in large ribbon mixers fitted with load cells and sampling ports. Moisture levels in dried inclusions are measured by infrared sensors before dosing. Sealing strength of foil lids is tested by applying standardized pressure until rupture. Seal failures beyond tolerance trigger immediate alarms. The entire production process is managed through a distributed control system, DCS. Each major component, mixers, fryers, fillers, lid sealers, labelers, is equipped with a PLC. These units communicate with a central control interface where operators can monitor flow rates, dough temperature, oil usage, fill weights, and output speed. Recipes and production profiles are saved digitally, allowing fast switchover between flavor variants or cup sizes. Sanitation is performed on a rotating schedule. Between shifts or recipe changes, dough mixers and noodle rollers are cleaned with high-pressure water and food-safe detergents. Fryers are drained and flushed with flushing agents. Dosing systems for powders and inclusions are disassembled and brushed manually. Cup molds and conveyors are wiped down using alcohol-based surface cleaners. Durum wheat semolina is the primary raw material used in pasta manufacturing. It arrives in bulk and is unloaded into stainless steel silos equipped with aerators and sifters. These silos store the semolina under controlled temperature and humidity. From the silos, semolina is conveyed pneumatically into a weigh hopper, where precise quantities are measured before entering the mixing system. Water is added to the semolina through a dosing pump as both ingredients enter the horizontal pre-mixer. The water is filtered and temperature controlled to ensure consistent dough development. The pre-mixer is a twin-shaft system with overlapping paddles that combine the semolina and water into a crumbly, granular dough. This stage typically lasts for 10 to 15 minutes, and no gluten is developed here, only hydration. The hydrated mixture then flows into a vacuum kneading chamber. This vessel contains a large screw auger that compresses and kneads the dough under vacuum. Air is evacuated to eliminate oxidation and reduce bubbles in the final product. Under pressure, the dough begins to form a cohesive, elastic mass. The kneading screw pushes the dough forward into the pasta press. The pasta press consists of a compression screw housed in a barrel. As the screw rotates, it applies mechanical pressure, forcing the dough forward toward the die head. Just before extrusion, the dough passes through a second vacuum chamber that removes residual air. This double vacuum system ensures smooth surface texture and prevents breakage during drying. The die head holds a brass or Teflon-coated die plate with dozens of holes shaped according to the type of pasta being produced: spaghetti, penne, fusilli, farfalle, or others. As the dough is pushed through the die, it takes on the corresponding shape. For shortcut pasta, like penne or rigatoni, a rotating blade mounted just beneath the die slices the extruded strands at uniform lengths. Blade speed and position are adjustable to control piece size. Immediately after cutting, the pasta falls onto a vibrating belt that separates and aligns the pieces. The belt feeds into a pre-dryer, a short chamber with warm air at low humidity. Here, the surface moisture is reduced to prevent sticking and deformation during handling. This stage lasts only a few minutes, but it's crucial for shape retention. For long-cut pasta, like spaghetti or fettuccine, strands are laid continuously onto rods or loops by an automated looping device. These rods are transported by conveyor into multi-stage dryers. The entire drying process is tightly regulated. Primary drying begins in a chamber where temperature and relative humidity are gradually increased. Warm air, typically between 55 degrees Celsius and 75 degrees Celsius, circulates through the pasta via fans and ducting systems. The airflow direction alternates to ensure even drying. Sensors monitor surface moisture content, and the pasta's structure begins to stabilize. In the next phase, stabilization, the temperature is held steady while humidity is slowly reduced. This allows the interior of the pasta to release moisture at the same rate the surface loses it, preventing cracks and internal stress. Each dry zone has PID controllers that adjust heat and airflow in response to real-time sensor feedback. The final phase, cooling, brings the pasta down to ambient temperature using filtered, dehumidified air. For long pasta, the hanging rods pass through these zones slowly over 6 to 10 hours. Shortcut pasta is dried on vibrating trays or mesh belts in large cabinet dryers that rotate trays periodically for even exposure. After drying, long pasta is automatically lifted from the rods and cut to standard retail lengths, usually 25 centimeters. The cut strands fall gently onto conveyor belts equipped with brushes that remove excess flour and broken tips. The pasta is then transferred to a vibrating sifter that separates any fines or small fragments. Short pasta, once dried and cooled, is conveyed into a series of screens and classifiers. Pieces outside the tolerance range, too short, broken, or malformed, are diverted to rework bins. Accepted product moves on to weighing and packaging. For packaging, pasta is first collected into hoppers above a multi-head weigher. These weighers use load cells and sensors to release exact quantities, 250g, 500g, or 1 kilogram, into form fill seal machines. Plastic film from large rolls is drawn into a forming collar and sealed around the falling pasta. Vertical sealing bars close the side, while horizontal sealing jaws crimp and cut the top and bottom. During sealing, vacuum nozzles or nitrogen flushing may be used to displace ambient air, extending shelf life. As each bag is formed and sealed, it passes beneath an inkjet printer that applies batch codes and expiration dates. Optical readers verify that print is clear and correctly positioned. For pasta sold in boxes, a different system is used. A volumetric filler dispenses pasta into an open-top carton traveling on a belt. Flaps are folded and glued by rotating arms, and the filled cartons pass through compression belts to ensure a tight seal. All packages, regardless of format, are collected into groups using collators. They are placed into corrugated cases by robotic case packers. Each case is built automatically from flat blanks sealed with hot melt glue and labeled using a print and apply labeler. Barcode scanners verify case content before palletizing. At the palletizing station, articulated robotic arms use vacuum grippers to pick and stack cases onto wooden pallets. Patterns are adjusted depending on case size and weight. Slip sheets may be inserted between layers for added stability. Once a pallet reaches full height, it is wrapped in stretch film using a turntable or robotic arm wrapper. The wrapped pallets are labeled and scanned into the warehouse inventory system. Forklifts or automated guided vehicles, AGVs, move the pallets to staging areas for outbound shipping. Throughout the process, quality control systems operate continuously. Semolina is analyzed for protein content, granule size, and moisture before use. Dough hydration is monitored using inline sensors that measure torque and consistency during mixing. Pasta diameter, wall thickness, and length are checked by laser micrometers at multiple stages. Moisture content in finished pasta is tested using infrared drying units or moisture balancers. Samples are also tested for cooking time, firmness, and swelling index. If any deviation occurs, the batch is flagged and removed from production. Clean in place, CIP, systems clean the dough mixers, extruders, and piping between production runs. Dry areas, like dryers and sifters, are cleaned manually using compressed air, brushes, and vacuum systems. Hygiene protocols are rigid to prevent contamination between product types. Die plates are removed and cleaned with pressurized water and ultrasonic tanks. Every die is catalogued and rotated based on shape and wear rate. Teflon-coated dies produce smoother pasta surfaces, while bronze dies give a rougher texture preferred for sauce adhesion. Air used in drying and cooling is filtered and conditioned. HEPA filters remove particulates, while dehumidifiers ensure consistent airflow. Each dry zone is mapped for temperature and humidity uniformity, using multiple sensors connected to a centralized control system. The entire production line is governed by a SCADA, supervisory control and data acquisition system. Operators monitor flow, pressure, motor speed, and temperature in real time from touchscreen panels. Recipes for each pasta shape are stored digitally and recalled instantly during changeovers. Mechanical actuators adjust die plates, blade positions, and packaging formats based on the selected recipe. Ingredient handling is fully automated. Semolina flows from silos through sealed conveyors. Water is filtered, dosed, and monitored with UV sterilizers and flow meters. Lubricants used in machines are food grade and monitored to prevent cross-contamination. Production runs are planned in batches, but the process is continuous. Pasta moves through mixing, extrusion, drying, and packaging without interruption. Only during scheduled maintenance or product changeovers does the line stop. From flour to fork, pasta manufacturing is a highly engineered sequence of mechanical, thermal, and pneumatic operations. Dough becomes structured through pressure and hydration. Shapes are formed under vacuum and cut by precision blades. Moisture is drawn out gradually in chambers humming with air currents. Machines fill, seal, stack, and wrap, synchronized by sensors and driven by control logic. Macaroni and cheese manufacturing begins with the continuous production of elbow macaroni, the signature pasta shape. Durum wheat semolina is stored in sealed silos where it's kept under controlled humidity and aeration. The semolina is pneumatically conveyed to a weigh hopper, then released into a high-speed horizontal pre-mixer. As the mixer runs, filtered water is injected in precise amounts through a flow-controlled nozzle system. The mixture forms a coarse, granular dough with no gluten development at this stage. The moistened dough transfers to a vacuum kneading chamber. Here, a slow-turning screw applies pressure to compress the particles into a cohesive mass. A vacuum pump removes excess air, preventing oxidation and ensuring the pasta will have a smooth surface and uniform color. The dough advances through a compression auger toward the pasta press. At the end of the press, the dough passes through a forming die. For elbow macaroni, the die includes a curved extrusion channel that forces the dough into a bent tubular shape. As the pasta is pushed through, a rotating knife cuts the curved tubes at uniform intervals. Blade speed is adjusted in coordination with dough pressure to maintain consistent piece length, typically around 2.5 to 3 centimeters. Freshly extruded macaroni is fragile and contains residual moisture. It is transferred by vibrating conveyor into a pre-dryer. This chamber uses warm, low humidity air to gently reduce the surface moisture and fix the shape. This step lasts 1 to 3 minutes and stabilizes the pasta for handling. The pre-dried pasta moves to a vibrating spreader that distributes it across a mesh belt, feeding into a multi-zone drying chamber. Inside the dryer, temperature, humidity, and airflow are carefully regulated. The first zone heats the pasta to 65-80 degrees Celsius, beginning internal moisture reduction. Airflow alternates above and below the mesh to dry evenly. In the middle zones, humidity is decreased gradually while heat is maintained. This balance prevents surface hardening or internal cracking. The final zone is a cooling section. Here, filtered ambient air lowers the temperature of the pasta to prevent condensation and to prepare it for packaging. Total drying time ranges from 4 to 8 hours, depending on pasta diameter, density, and production volume. The dried macaroni is discharged onto vibrating sieves that remove any undersized or broken pieces. Acceptable product moves by conveyor to a vertical bucket elevator, lifting it into a hopper above the packaging line. From here, pasta is fed into multi-head weighers that release fixed quantities, typically 200 g to 400 g, into individual pouches. While pasta is being processed, cheese powder mix is prepared in a separate blending operation. Ingredients including dehydrated cheese, whey, milk solids, salt, sodium phosphate, citric acid, and annatto are dosed from stainless steel silos and hoppers into a ribbon blender. The blender combines the powders using overlapping blades that tumble the mix in opposite directions. Uniformity is critical. Each pouch must contain identical flavor and solubility properties. After blending, the cheese powder is sifted through a vibratory screen to remove agglomerates. It is then conveyed to a secondary packaging station. A separate form-fill seal machine doses a measured amount of cheese powder, typically 20 g to 30 g, into heat-sealed pouches made from laminated film with oxygen barrier properties. Each pouch is coded with batch and expiration data and conveyed for integration with the pasta. In the combination stage, one pasta pouch and one cheese powder pouch are merged. Collation conveyors synchronize both lines, bringing pasta and cheese pouches together just before cartoning. A horizontal cartoning machine erects cartons from flat blanks, folds the bottom flaps, and holds them open with mechanical fingers. A robotic arm inserts the combined pouches into each open carton. Once filled, the top flaps are closed and sealed using hot melt glue. As cartons exit the sealing station, inkjet printers apply product codes, date stamps, and barcodes. Cameras verify code presence and alignment. Rejected cartons are automatically diverted to a separate line for inspection or rework. Correct cartons proceed to case packing. Cartons are grouped using an inline collator and pushed into a corrugated case supplied by an automatic case erector. Hot glue or tape is applied and the flaps are sealed. Each case passes through a check weigher to verify total contents and is labeled with a print and apply system. The label includes product ID, case count, and tracking data. At the palletizing station, robotic arms stack sealed cases onto wooden pallets. Vacuum pads or gripper arms lift and rotate boxes into aligned layers. Slip sheets are inserted automatically every few layers for added stability. Completed pallets move to a stretch wrapping turntable, where film is wrapped around the load under controlled tension. While packaging is underway, the dry blend operation also prepares bulk cheese powder for institutional or bulk formats. In this variation, cheese mix is loaded into large gusseted bags or drums. Powder filling machines operate under HEPA-filtered enclosures to control dust. Filled bags are sealed with continuous band sealers and printed with lot codes before being packed into master cases. Raw materials for both pasta and cheese powder are delivered in bulk and undergo stringent intake controls. Semolina is tested for protein content, ash level, and granulation. Cheese powder inputs are sampled for moisture, pH, and flavor profile. Silo inventory levels are managed using load cells and level sensors. Water for dough mixing is filtered, UV treated, and temperature controlled. Air used in dryers and conveyors is HEPA filtered and dehumidified. Oil lubricated machinery in contact with product zones uses food-grade lubricants only. All processing equipment is stainless steel, with sloped surfaces and minimal joints to aid cleaning. Production lines are monitored through a central PLC-based control system. Operators use touchscreens to set parameters for extrusion pressure, knife speed, dry temperatures, fill weights, and glue patterns. All parameters are saved in production recipes, enabling rapid line changeovers for different pack sizes or formulations. Extruder head pressure, dough torque, and vacuum levels are logged continuously. Dryer systems include multiple thermocouples and humidity sensors managed by PID loops for responsive control. Air velocity through the drying chamber is measured and adjusted automatically to prevent temperature layering or hotspots. Clean-in-place systems are used to sanitize closed-loop components such as pasta augers, cheese, mix lines, and filler hoppers. Open surfaces are cleaned during scheduled downtime with pressurized water and food-safe detergents. Verification is conducted using swab tests and ATP monitors. Quality control is integrated throughout the line. Pasta is inspected for length, curl radius, color, and residual moisture. Laser micrometers measure wall thickness and internal diameter. Finished pasta is tested for cooking yield, firmness, and disintegration resistance. Cheese powder is evaluated for blend consistency, flavor, and solubility. Random packs are rehydrated and cooked to simulate consumer preparation. Packaging integrity tests include burst tests, seal strength, and vacuum retention for pouches. Cartons undergo drop testing and compression tests to ensure they withstand transit conditions. For single-serve or microwavable mac and cheese, the process begins similarly with pasta production. However, instead of dry packaging, cooked pasta is used. The pasta is first boiled in industrial cookers, long troughs with recirculating hot water systems. After cooking, pasta is cooled rapidly in rotary chillers with cold water spray and air blowers. Cooked pasta is dosed directly into plastic microwavable cups or trays using multi-head filling machines. Cheese sauce, prepared in heated kettles, is pumped into a separate filling head. The sauce is hot-filled immediately after preparation, using servo-controlled pistons that regulate volume and flow rate. After filling, the trays or cups are sealed with foil lids using heated platen sealers. Lidded units are passed through a tunnel pasteurizer, where steam or hot water raises the internal temperature to sterilize the contents. After pasteurization, the products pass through a cooling tunnel with chilled air to bring them to ambient temperature for packaging. Microwavable cups are labeled with shrink sleeves or wraparound labels. Each unit is inspected for fill level, lid seal, and label alignment. These are packed into display cartons, cased, palletized, and shipped with the same downstream systems as dry pack boxes. From raw wheat and powdered cheese to complete boxed or ready-to-eat products, mac and cheese production is a tightly orchestrated process of extrusion, drying, blending, dosing, and packaging. Each component, elbow macaroni and cheese powder, follows a distinct line until their paths converge. Machines extrude thousands of macaroni tubes per minute, slice them, dry them, and screen them into uniform shapes. Ribbon blenders tumble cheese powder until it's perfectly homogeneous. Pouches are filled, sealed, combined, and boxed with mechanical precision. Candy corn has been called everything from iconic to controversial, but love it or hate it, there's no denying its place in the candy world. Every fall, manufacturers churn out over 35 million pounds of it. That's around 9 billion individual kernels, just in time for Halloween. And despite its soft, waxy texture and sugary simplicity, candy corn is a surprisingly complex product to make. Each tiny triangle has 3 distinct layers, molded by hand in the early days, but now mass-produced by a system of pumps, molds, and precision timing that dates back over a century. The process starts not with sugar, but with syrup. Lots of it. Candy corn's signature texture comes from a combination of corn syrup, sugar, and confectioner's glaze, plus stabilizers like gelatin and fondant. These ingredients are pumped into massive stainless steel cookers, where they're heated and stirred into a thick, golden mixture. The heat is just high enough to dissolve the sugar and activate the gelatin, but not so high that it starts to brown or caramelize. This syrup is sticky, slow-moving, and heavy, about the consistency of warm honey. Industrial agitators churn constantly to keep the blend smooth and uniform. At this stage, it's just base candy mass, flavorless, colorless, and pale. Once the syrup reaches the right temperature and consistency, it's pumped through insulated tubes into holding tanks, where it will be divided and dyed into the 3 iconic candy corn colors: white, orange, and yellow. Each color batch is handled separately. Dyes and artificial flavorings, vanilla being the most common, are mixed in while the syrup is still warm and fluid. The bright orange and deep yellow hues come from synthetic food colorings added in highly controlled amounts. Because each layer of a candy corn kernel needs to hold its shape, the timing of the cooling and pouring is crucial. Too runny, and the colors bleed together. Too thick, and the candy won't mold properly. And now comes the most fascinating part, the starch molding process. Unlike hard candies or chocolate, which are poured into metal molds, candy corn is made using cornstarch trays, a method known as mogul molding. This technique dates back to the 1800s and was originally used for gumdrops and jellies. In this process, wooden or plastic trays are filled with a smooth layer of cornstarch, and a metal stamp, shaped like a kernel of corn, presses down into the starch to create thousands of tiny impressions. These impressions become the molds. The cornstarch serves 2 purposes. It shapes the candy, and it wicks away moisture as the candy sets. It also prevents sticking, allowing the soft candy to be poured into molds without clinging to the sides. The candy corn syrup, now colored and flavored, is loaded into 3 separate heated hoppers. Each hopper is connected to a nozzle that moves across the tray like a printer head. First, the yellow syrup is deposited into the bottom of the mold, forming the wide end of the kernel. Next, the orange layer is piped on top of the yellow. Finally, the white tip is added, capping the candy and completing the familiar tricolor pyramid. What's amazing is how fast this happens. The nozzles move with millimeter precision, depositing the candy in timed bursts so the layers stack cleanly. The entire process is automated, with vision systems ensuring each layer is aligned. If the syrup is too hot, the colors run. If it's too cool, the layers sit unevenly. Operators monitor flow rate, temperature, and color alignment in real time. A misalignment of even a few millimeters means the piece gets rejected. Once deposited, the trays are stacked and sent to a drying room. Here, warm air circulates gently through racks of cornstarch trays, allowing the candy to firm up over the course of 24 to 36 hours. This slow drying process lets the gelatin set fully and gives candy corn its firm, chewy bite, somewhere between a marshmallow and a fudge. During this phase, the moisture content drops, and the surface forms a skin that will later be sealed by a glaze. After drying, the trays are sent through a sifting machine, a kind of giant mechanical sieve that gently shakes the candies loose from the starch. Fine brushes remove any residual powder, and the candy corn kernels tumble out, fully formed and nearly ready. The used starch is vacuumed up, filtered, and reused again and again. Next comes glazing, which gives candy corn its slight shine and distinctive feel. The candies move into a rotating pan, a giant drum that looks like a horizontal cement mixer, where they're tumbled gently with confectioner's glaze, also known as shellac. This glaze is made from natural resin and gives the candy its smooth, slightly waxy surface. It also helps lock in moisture and extends shelf life. The glaze is sprayed in fine mist over the tumbling candies, coating them evenly as they spin. A final dusting of mineral oil or carnauba wax is sometimes added to improve shine and reduce stickiness. Then the candy is cooled once more to allow the coating to set. From here, the finished candy corn travels down the line to inspection and sorting. Modern candy corn lines use cameras and sensors to scan each kernel. Broken pieces, fused clusters, or misaligned colors are detected and diverted. Only those with the perfect layered look and proper size continue on to packaging. Packing is done by volume, not weight. Because each piece is roughly identical in size and density, volumetric fillers can quickly drop the exact number of pieces into each bag. The candy moves into plastic film pouches that are formed, filled, and sealed in rapid succession. Some lines package candy corn into plastic pumpkins or tubs for bulk sales. Others drop the kernels into small Halloween treat bags or multi-pack gift assortments. Each package is date-coded and batch labeled for traceability. The packaging lines operate at high speed, up to 200 bags per minute, and are checked frequently for weight, seal integrity, and print clarity. Rejects are automatically pushed off the belt for rework or recycling. Meanwhile, quality control teams sample pieces from each batch throughout the day. They test for moisture, color accuracy, texture, and flavor. Batches that fall outside the tolerance window are flagged and removed. And it doesn't stop there. Shelf life tests simulate long-term storage to ensure that even months later, the candy corn remains soft in the center, dry on the outside, and bright in color. Behind all this is an incredibly clean operation. Corn syrup and sugar are magnets for microbes and insects, so sanitation is constant. Lines are cleaned daily with food-safe cleaners. The starch trays are sterilized and filtered between uses. Air in the drying rooms is HEPA filtered and climate controlled. Workers wear full-body suits, gloves, and face coverings. Even the starch used in molding is monitored for moisture and contamination. And although candy corn is mostly associated with Halloween, production runs year-round. Some factories operate multiple lines, each dedicated to a different variation, like Indian corn with a brown chocolate base, pastel-colored spring corn, or red and green Christmas corn. Each variation uses the same molding method, but with different dyes and flavor oils. What makes candy corn truly unique in the candy world is how little it's changed over the past century. While most candies chase trends or lean into bold packaging and fusion flavors, candy corn has stuck to the same 3-layer formula. It's still molded in starch trays, still glazed with shellac, still wrapped in bags with smiling jack-o'-lanterns and autumn leaves. And yet, the engineering behind it, fluid dynamics, time deposition, layered cooling, makes it anything but simple. From syrup to striping, from molds to glaze, candy corn is built through a process of timing, precision, and surprisingly delicate handling. It's a candy that's soft but structured, seasonal but industrial, polarizing but unmistakable. Red vines might look like just another chewy red candy, but behind every twisty, glossy rope is a process built on timing, texture, and tradition. They don't snap like hard candy. They don't melt like chocolate. Instead, red vines land right in the middle, soft but sturdy, sweet but mild, with that unmistakable red flavor that somehow doesn't match anything in nature, but still feels oddly nostalgic. And every piece is extruded, cut, cured, and packed in a factory where thousands of pounds of chewy candy are born each day, one vine at a time. The process starts with wheat flour. Yes, flour. Unlike many chewy candies that rely heavily on gelatin, red vines begin with a dough-like base that's more similar to soft pasta or bread than taffy or gummies. That flour gives red vines their subtle chew, the kind that resists just enough to make it satisfying without sticking to your teeth. Large silos hold finely milled wheat flour, which is fed via vacuum tubes into massive stainless steel mixers. Here, flour meets corn syrup, sugar, water, salt, and a mix of colouring and flavouring agents. The exact formula is a tightly guarded secret, but the result is a sticky, pink-red dough with the consistency of warm modelling clay. This mixture isn't cooked in the traditional sense. Instead, the ingredients are combined cold, then heated just enough to activate the flour and dissolve the sugars. Once mixed, the dough is kneaded and allowed to rest. This step helps hydrate the flour and develop the right elasticity. In large batches, resting lets the starches soak up moisture, creating that soft yet dense chew red vines are known for. Then the dough is transferred to a giant hopper above the extrusion line, a machine that plays the starring role in the entire operation. Extrusion is the core of red vines production. A heavy-duty screw pushes the dough through custom steel dies, metal plates carved with the exact shape of the candy. Each red vine emerges from its die already formed, hollow inside, ridged on the outside, and perfectly round. The hollow center isn't just for show. It speeds up the cooking and drying process and gives the candy that unique bend and bounce. As the ropes emerge, they're still warm and slightly sticky. They travel along a cooling conveyor, which slowly brings the temperature down and firms up the texture. Air circulates over the ropes in controlled patterns. Too much airflow and the vines dry unevenly. Too little and they stick to the belts. Fans hum, belts glide, and the factory fills with a warm, sweet smell. Somewhere between cotton candy and strawberry preserves, with just a hint of flour dust in the air. Once cooled, the vines are trimmed by a high-speed cutter that slices each rope to the exact retail length. The ends are sealed as they're cut, creating clean, smooth tips. Waste from trimming, tiny nubs and offcuts, are collected, melted back down, and returned to the mixer. Almost nothing goes to waste. Now comes the curing phase, and it's the part most people don't realize exists. Freshly extruded red vines are chewy, but lack the finished texture. To get that signature snap resistance and balanced bite, the candy is placed in curing rooms, temperature and humidity controlled chambers, where the vines rest for several hours to several days. During this time, moisture migrates evenly through the candy, and the surface forms a delicate skin. It's this curing step that sets red vines apart from similar licorice-style candies, which are often either sticky or brittle right off the line. Inside these rooms, racks of trays hold thousands of red vines at once. Air is circulated and filtered to prevent microbial growth. The relative humidity is kept within a narrow band, typically around 45-55%, to ensure consistent texture without drying out. Operators regularly test sample pieces for bend, bite, and density. Too soft? Extend the cure. Too hard? Adjust the airflow. It's a constant dance between science and feel. Once the candy has cured, it's time for packaging. Red vines are known for their classic plastic tubs, trays, and theatre boxes. Each format requires a different handling system, but they all start the same way: counting. Red vines aren't sold by weight, they're sold by count. Whether it's a tray of 12, a tub of 240, or a twin pack of 4, machines must measure and deliver the exact number of vines per unit. Vision systems and laser counters confirm that each group contains the right amount, and robotic arms stack the vines into trays or drop them into clear plastic tubs with incredible speed. For tubs, the lid is heat sealed with a plastic film before snapping into place, an airtight barrier that locks in freshness. For individual trays, a roll of printed plastic film wraps around the product and is heat sealed at both ends, forming a tight package with a familiar crinkle. Boxes are assembled, filled, sealed, and coded with best by dates and batch numbers. Throughout the entire process, quality control teams pull samples every 30 minutes. They check for moisture, color consistency, elasticity, and flavor balance. One test involves bending a vine to a specific angle. If it breaks too easily, it fails. If it stretches too far, it's too soft. Another test checks surface stickiness under controlled conditions. Too much tack? It could be a temperature error during extrusion. Too dry? Likely an airflow issue during curing. And the flavor? Well, that's another mystery. Unlike cherry, strawberry, or raspberry, red vine's flavor is simply known as original red. It's not based on any real fruit, and it doesn't try to be. It's its own thing. A light, semi-sweet profile with mild floral notes and a faint trace of licorice root. The flavor is added during mixing and must survive the entire extrusion and curing process without degrading. So it's formulated to withstand heat, moisture shifts, and long shelf life. That flavor balance is monitored constantly. Flavor oils are tested for purity and potency. If a batch comes in even slightly out of spec, it's adjusted before hitting the mixer. Consistency is king, no matter where you buy them. California, New York, or overseas, a red vine should taste exactly like it did in your childhood movie theater. Sanitation in the factory is tight. Because the product is wheat-based, every surface must be scrubbed to prevent gluten buildup, mold risk, or microbial contamination. Workers wear gloves, smocks, and hairnets. Machinery is cleaned daily, and the extrusion lines are taken apart and sanitized on a strict schedule. Every hose, belt, and die plate is made of food-grade material and built for quick disassembly. And because red vines contain no gelatin or animal-derived ingredients, they're certified vegan, a point that adds another layer of control. No cross-contact with animal-based materials is allowed in the facility, even for other products. The whole operation is designed for purity, consistency, and speed. Production runs year-round, not just for the iconic red. Red vines also come in black licorice, made with real licorice root extract, grape, cherry, and seasonal flavors. Each variant has its own dye blend and curing profile. Some need more moisture, others less. Switching from one flavor to another requires a full line purge and sanitation cycle, followed by calibration of the extrusion and curing parameters. Every Tootsie Roll starts its life in a factory designed for one specific purpose: to transform raw, shelf-stable ingredients into a soft, chewy candy with a shelf life that can stretch over a year. It's a factory that never deals in chocolate tempering or delicate sugar glass. Instead, it deals in heat, pressure, and mechanical precision, designed to produce millions of pieces per day without changing the formula that's been running for more than a century. The process begins at the ingredient silos, tall, stainless steel tanks that hold the building blocks of the candy: sugar, corn syrup, condensed skim milk, cocoa, palm oil, and whey. Everything arrives in bulk. Dry ingredients are stored in sealed hoppers and vacuum fed to the mixing line, while liquid ingredients are pumped through heated pipes to maintain flow. The factory is divided into zones, each temperature and humidity controlled to keep sugars from clumping or crystallizing before they even reach the cookers. The cooking zone is where the transformation starts. Giant stainless steel kettles, each several feet deep, combine the dry and wet ingredients. The sugar and corn syrup provide sweetness and the candy's dense structure. Condensed milk adds body and richness. Cocoa gives flavor and color, while palm oil delivers that slight, waxy mouthfeel and shelf stability. Heating coils beneath the kettles bring the mixture to high temperatures, typically above 245 degrees Fahrenheit. At this stage, the mixture is thick, brown, and glossy, similar in texture to hot fudge, but without any of the dairy-based volatility of real chocolate. Agitators, slow-turning steel paddles, continuously stir the mass, ensuring it doesn't scorch on the bottom or develop hot spots. The goal is to reduce the water content slowly while emulsifying the fats and sugars into a uniform, pliable base. The process is not just about cooking, it's about moisture control. Tootsie Rolls must be firm but soft, with a final moisture content that lands in a tight range, enough to stay chewy, but not so much that mold or microbial growth becomes a risk. Once the batch hits target temperature and consistency, it's pumped out of the kettle and onto a cooling table, a wide metal slab chilled from below. As the candy hits the surface, it begins to thicken. Factory workers use large metal paddles to fold the mixture over itself repeatedly. This aerates the mass slightly, allowing steam to escape, while also creating a uniform density throughout. The folding also gives the candy its familiar matte finish as it loses its shine and becomes a smooth, pliable block. Next comes batch, feeding into the extrusion system. Here, the candy is pressed into a hopper that funnels it into a long horizontal extruder. Inside, a rotating screw pushes the candy through a heated cylinder, keeping it at the perfect consistency for shaping. At the end of the extruder is a precision die plate, punched with holes the exact width and shape of a classic Tootsie Roll. As the candy is pushed through these dies, it forms long, continuous ropes. These ropes are laid gently onto conveyor belts, which carry them through a cooling tunnel, a controlled environment where the ambient air is dry and cool. This cooling phase is key to locking in the candy's shape and texture. If it cools too quickly, the surface becomes brittle. Too slowly, and the ropes sag and deform. So air is circulated in carefully mapped patterns, and conveyor speed is adjusted to match. At the end of the tunnel, rotary knives, mounted on fast-moving arms, slice the ropes into perfect lengths. These cutters use sensors to monitor rope speed and ensure that each piece is cut to the exact size, often within a fraction of a millimeter. The offcuts, end trims, and any malformed pieces are immediately collected and routed back to the rework system, where they're melted and remixed with the next batch. The wrapping line is a marvel of mechanical timing. Each unwrapped Tootsie Roll is picked up by a spinning arm and placed in the center of a piece of waxed paper. From there, automated fingers fold the paper and twist both ends in a single, fluid motion. The wax paper isn't just for nostalgia. It serves as a moisture barrier and keeps the candy from sticking to itself during storage. The machines that do this twist wrapping can handle thousands of pieces per minute, each one perfectly aligned and sealed. Wrapped pieces are fed into grouping chutes that divide the flow by packaging format. Some go into large bulk cartons for seasonal mixes or retail tubs. Others are diverted into form-fill-seal machines, which create bags on the fly from printed plastic film. The film is shaped into a tube, the bottom sealed, the candy dropped in, and the top sealed, cut, weighed, and printed with a batch number in one continuous motion. Each batch is logged and traceable. The factory uses inline quality control systems, scales, moisture sensors, and cameras to check random samples every few minutes. Each sample is tested for chewiness using pressure sensors, as well as for water activity, weight, and visual appearance. Batches that fall outside tolerance are flagged and either adjusted or scrapped. In the background, conditioning rooms play a silent but crucial role. Even after wrapping, the Tootsie Rolls go through a short curing phase, stored in a controlled space where the temperature and humidity allow residual moisture inside each piece to equalize. This gives the candy its signature consistency, a firm outer layer that gives way to a slow, even chew. It's not a soft candy, but it's never brittle. That balance is achieved not just through cooking, but through post-production conditioning. One of the most impressive parts of the Tootsie Roll line is how self-contained it is. Nearly every part of the candy's life cycle, from mixing to wrapping to packing, happens under one roof. There are no separate molding lines, no chocolate coating stations, no decorating robots. Just an endless rhythm of cooking, folding, extruding, slicing, and wrapping. Hygiene is meticulously managed. The production area is kept dry and sealed to prevent microbial growth. Since the candy contains dairy, cross-contamination risks are strictly controlled. Workers suit up in food-safe uniforms, pass through air showers, and sanitize hands before entering. All contact surfaces are cleaned and steamed daily. Even the air in the cooling tunnels is filtered and circulated through HEPA systems. The equipment is built for durability and repeatability. Extruder dies are machined from food-grade stainless steel and polished to reduce friction. Belts are anti-static and antimicrobial. The wax paper is fed from massive rolls and stored in temperature-controlled rooms to prevent humidity damage. Switching to other products like flavored Tootsie Rolls, vanilla, cherry, lemon, etc. requires a full line cleaning and rebalancing of the recipe inputs. Flavoring oils and colors are added just before the extrusion phase to preserve their strength. And because the base formula changes slightly with each flavor, extrusion temperature, conveyor speeds, and curing times are adjusted accordingly. Even waste is managed tightly. Scrap from offcuts, miswraps, and test samples are sorted and either melted back into the system or composted if outside of safe rework parameters. Nothing is sent to landfill unless absolutely necessary. At full capacity, a Tootsie Roll factory can produce tens of millions of pieces per day, each one a near-perfect replica of the one before it. And while the candy itself seems simple, the infrastructure behind it is built for complexity at scale. From heat management and moisture control to real-time mechanical adjustment, the factory is a living system, always running, always calibrating. So while the Tootsie Roll may not look high-tech or trendy, its production is a masterclass in controlled, repeatable food manufacturing. It's a candy built not for flash, but for function, shaped by a process that favors durability, stability, and total control from first pour to final twist. It all starts with malted barley, the soul of the beer. In a factory setting, the malt arrives by truckloads or freight trains already malted at a dedicated malting facility. Malting is a process in itself. Barley is soaked, allowed to germinate just enough to activate enzymes, and then dried and kilned to stop the growth. This controlled germination unlocks starches and enzymes that will later convert to fermentable sugars. The exact roast of the malt, pale, caramel, a chocolate, black, determines much of the final beer's color and flavor. For large-scale beers, base malts are used, usually lightly kilned, with small amounts of specialty malts blended in. The malt is piped into massive silos at the brewery, where it's stored dry and clean. When brewing begins, the malt is sent through a series of conveyors or airlifts to the mill. Here, roller mills crush the grain, not into flour, but into coarse grist. The idea is to crack the husk while leaving the interior accessible. Too fine, and the mash will become sticky and hard to filter. Too coarse, and sugar extraction drops. The grist is collected and weighed, then transported directly to the mash tun where the real transformation begins. In the mash tun, often a stainless steel vat the size of a swimming pool, the grist is mixed with hot water to form a thick porridge-like slurry. This step, called mashing, activates enzymes like amylase, which convert starches into simple sugars. The temperature is held precisely, usually around 65 and 68 degrees Celsius, depending on the style of beer. Too hot and the enzymes are denatured. Too cold and the starches won't fully convert. The mash is gently stirred using mechanical arms to ensure uniformity. For the next hour or so, the grain slowly transforms into a sweet liquid known as wort. When conversion is complete, the mash is transferred to the lautering vessel, sometimes built into the same tank. Lautering is the process of separating the liquid wort from the spent grain. A false bottom or fine slotted plates allow the liquid to drain through, while the grain bed itself acts as a natural filter. More hot water, known as sparge water, is sprayed over the top to rinse out every last bit of sugar. The collected wort flows to the brew kettle, while the spent grain, now protein-rich but sugar-poor, is conveyed out of the system. Many large breweries donate or sell this grain to farms as cattle feed. Next is the boil. In towering stainless steel kettles, the wort is brought to a rolling boil and held there for 60 to 90 minutes. This step sterilizes the liquid, halts enzymatic activity, and causes unwanted proteins to coagulate and fall out of suspension. It's also when hops are added. Hops are the cone-shaped flowers of the Humulus lupulus plant, prized for their bitterness, flavor, and aromatic oils. In a factory setting, hops usually arrive as compressed pellets for consistency. Early additions bring bitterness. Late additions and whirlpool hops contribute aroma and flavor. Boiling is carefully managed. A powerful steam jacket heats the vessel, while a system of condensers captures volatile compounds and steam vapor to reduce environmental impact. The smell during this stage is unmistakable. Sharp, herbal, sweet, and slightly pungent. It's the moment beer begins to take on its final character. After the boil, the wort must be rapidly cooled. This happens in a plate heat exchanger, where hot wort flows past cold water or glycol in alternating metal plates. Temperatures drop from near boiling to fermentation ready, usually between 10 degrees Celsius and 20 degrees Celsius, in just seconds. In most large breweries, the water used to cool the wort is captured and reused to preheat the next batch, conserving energy. From there, the chilled wort is transferred to fermentation tanks, colossal, conical bottom vessels made of polished stainless steel. Some are the size of small buildings. This is where the magic really happens. Yeast is introduced, either ale yeast or lager yeast. Yeast begins feeding on the sugars in the wort, producing alcohol and CO2 as byproducts. The tanks are fitted with sensors that monitor temperature, pressure, and gravity in real time. If fermentation is too vigorous, pressure is vented. If it's too slow, temperature can be nudged to wake up the yeast. Fermentation can last from a few days for ales to several weeks for lagers. During this time, brewers pull samples to test for alcohol levels, residual sugars, pH, and flavor development. In big factories, this data is fed into digital brewing systems that model yeast health and fermentation curves. If something's off, brewers are alerted immediately. Once fermentation is complete, the beer isn't quite ready. It must be conditioned, held at near freezing temperatures to clarify and stabilize. During this stage, yeast settles out, flavors mellow, and carbonation levels are adjusted. Some factories use centrifuges to speed clarification. Others rely on time and gravity. Filtration may be employed, either with diatomaceous earth, membranes, or cross-flow systems to remove fine particulates and ensure brilliant clarity. For beers that are meant to be bright and shelf-stable, pasteurization may follow, either flash pasteurization or tunnel pasteurization. But not all beer is pasteurized. Many craft style or draft-only products skip this step to retain delicate aromas. Once the beer is bright, cold, and stable, it's ready for packaging. In large breweries, packaging lines are like choreographed metal highways. Bottling lines can run at 1,200 bottles per minute. Can lines are even faster. Kegs are cleaned, filled, capped, and labeled by machines. Bottles are rinsed, filled under pressure to avoid foaming, sealed with crown caps, and passed through date coders and labelers. Cans are seam locked, rinsed, and pressure checked. Every container is sampled for fill height, oxygen pickup, carbonation, and microbial safety. In some facilities, advanced cameras scan every bottle or can for imperfections in milliseconds. The packaging halls are cold, loud, and almost hypnotic. Conveyor belts twist and curve. Robotic arms stack cases onto pallets. Shrink wrap machines seal entire loads for distribution. Forklifts or automated guided vehicles shuttle product to cold storage, where beer awaits distribution to bars, grocery stores, sports stadiums, and corner shops around the world. But behind the machinery is a deeper layer of quality assurance. Beer is a living product, and even at massive scale, breweries run labs that would rival pharmaceutical facilities. There are microbial labs, sensory panels, gas chromatographs, and mass spectrometers analyzing aroma compounds, esters, sulfur levels, and oxygen ingress. Trained tasters, often called sensory analysts, taste beer daily, blind, and score it against reference samples. A slight change in carbonation or hop aroma is enough to flag a batch for review. And hygiene is non-negotiable. Brewing equipment is cleaned constantly with clean-in-place systems that circulate caustic solutions, acid rinses, and sanitizers through every pipe, pump, tank, and valve. Breweries are designed with sloped floors, airlocks, positive pressure rooms, and filtered ventilation to minimize contamination. Yeast cultures are kept in pure, cryogenically preserved banks and propagated in sterile fermenters. Even the water is treated, filtered, softened, and dechlorinated to ensure it doesn't introduce off flavors. Despite the scale, there's a strange elegance to the whole system. Every tank, pump, sensor, and pipe is part of a carefully designed loop. From raw grain to finished beer, the factory operates almost like an ecosystem, closed, balanced, and tightly monitored. Nothing is left to chance. Even the CO2 released during fermentation is often captured and reused to carbonate the final product, reducing waste and environmental impact. Bacardi all starts with molasses, a byproduct of sugar refining. Once cane juice has been boiled and crystallized into sugar, what remains is a dark, viscous liquid rich in residual sugars and minerals. Bacardi sources its molasses primarily from the Caribbean and Central America, where sugarcane grows in abundance. Shipments arrive by the ton, offloaded into deep storage tanks that keep the molasses warm and pumpable. Its smell is rich and heavy, deeply sweet, slightly sour, with a roasted, almost smoky undertone. Before fermentation begins, the molasses is diluted with pure water and combined with nutrients to prepare what's known as the fermentation wash. Bacardi uses a proprietary strain of yeast, one that's been carefully preserved and propagated for generations. This yeast is key. It's what gives Bacardi its distinctive profile: clean, light, with subtle fruity esters and very low levels of fusel oils. In a dedicated propagation room, yeast cells are grown in increasingly larger vessels, fed on molasses and oxygen, until they're strong enough to handle full-scale fermentation. The prepared wash, diluted molasses, nutrients, and yeast is pumped into fermentation tanks, towering steel vessels the size of small silos. Fermentation is fast and efficient, typically 24 to 30 hours. During that time, the yeast devours the sugars, converting them into alcohol and CO2. The temperature is carefully regulated. Too hot, and the yeast dies. Too cold, and it underperforms. Sensors monitor every parameter in real time: sugar levels, temperature, pH, alcohol content. In massive control rooms, technicians watch digital dashboards as each tank ferments with machine-like consistency. The result of this stage is not rum yet. It's a low alcohol liquid called wash or beer, usually around 7 to 10% ABV. It smells nothing like rum. It's sweet, funky, raw. To transform it into the clear, potent spirit known around the world, Bacardi moves to the next phase: distillation. Distillation is where alcohol is concentrated and flavors are defined. Bacardi doesn't rely on pot stills, as many small batch rums do. Instead, it uses continuous column stills, tall, multi-stage distillation towers that can separate alcohol with incredible precision. These columns have trays or packing materials inside that force the vapor and liquid to interact repeatedly, concentrating the alcohol while removing unwanted compounds. The fermented wash is pumped into the column, heated from the bottom, and as it rises, different components evaporate at different heights. Light, clean alcohols rise to the top and are collected. Heavier compounds are left behind and drained off. By adjusting the temperatures and reflux ratios, Bacardi's distillers control the exact cut of alcohol they want to keep. The result is a high-strength spirit, often 85% ABV or higher, that's clear, light, and extremely pure, essential for Bacardi's signature smoothness. But pure alcohol isn't rum yet. The next steps, aging, blending, and finishing, are where the artistry comes in. The raw distillate, also called aguardiente, is diluted down to around 60 to 70% ABV and pumped into oak barrels for aging. Bacardi primarily uses used American white oak barrels, many of which once held bourbon. These barrels are charred on the inside, and over time, they impart color, vanilla notes, spice, and tannins to the rum. In Bacardi's aging warehouses, massive barrel halls with racks stacked to the ceiling. Tens of thousands of casks rest in the tropical heat. The climate speeds the interaction between spirit and wood, making even short aging periods highly effective. Different rums are aged for different durations. Bacardi Superior, the classic white rum, may be aged for as little as 1 year before being filtered. Gold and flavored varieties rest longer. Premium products like Bacardi 8 or Bacardi Reserva Limitada are aged 8 to 12 years or more. Each barrel breathes. Alcohol evaporates, a phenomenon known as the angel's share, and oxygen seeps in. Over time, harsh edges soften, flavors deepen, and the rum becomes increasingly complex. Once aging is complete, barrels are emptied, and the rum is evaluated. This is where Bacardi's master blenders, trained experts who can detect flavor differences down to the subtlest note, step in. Dozens, sometimes hundreds of barrels are selected and blended together to create a final product with exactly the right profile. Some rums bring fruity notes, others deliver weight or spice, others still provide structure or sweetness. The blender's job is to make the sum better than the parts, and to ensure that every bottle tastes exactly like the last one, year after year. Now comes one of Bacardi's most distinctive processes, charcoal filtration. For Bacardi Superior and other light rums, the blended rum is passed through layers of activated charcoal, often made from coconut husks, to remove color and certain heavy flavor compounds. This process, inspired by Don Facundo Bacardi himself in the 1860s, strips away rough edges and leaves the rum bright, clean, and smooth. Even after aging in oak, the charcoal returns the rum to a near-clear appearance while preserving its vanilla and almond undertones. Once filtered, the rum is diluted with ultra-pure demineralized water down to bottling strength, usually 37.5% or 40% ABV, depending on the market. It's then passed through fine mesh filters to remove any remaining particles, chilled to encourage clarity, and tested for stability. Quality checks are constant. ABV, color, turbidity, aroma, flavor, all are measured in both labs and sensory rooms. Finally, the rum is ready to be bottled. Bacardi's bottling lines are massive, high-speed operations, capable of producing tens of thousands of bottles per hour. Empty glass bottles, custom-shaped with embossed bats and logos, are automatically loaded onto conveyors. They're rinsed, filled with rum under pressure, sealed with tamper-proof caps, and labeled with laser precision. Date codes are printed, barcodes are verified. Every bottle passes through inspection tunnels equipped with cameras and sensors to catch defects, underfills, or misplaced labels. From there, bottles are packed into cartons by robotic arms and shrink-wrapped onto pallets. Pallets are barcoded, logged, and stacked in warehouse zones ready for distribution. Bacardi's logistics network spans continents. From a single facility, trucks, ships, and containers move product across the globe. To supermarkets in Spain, beach bars in Brazil, nightclubs in New York, and resorts in Thailand. Behind the scenes, sustainability plays an increasing role. Many of Bacardi's distilleries use renewable energy, recycle processed water, and recover CO2 from fermentation. Spent yeast and distillation byproducts are often converted into animal feed or used in bioenergy systems. Even the barrels, when retired, may be repurposed for furniture, flooring, or smaller barrel aging projects. Waste reduction is not just about economics. It's part of preserving the legacy of the land and the product itself. And yet, for all this technology and scale, Bacardi's rum still carries with it a certain history, a sense of origin. The company was founded in 1862, and though exiled from Cuba in the 1960s, its roots remain in the tropics. The smoothness of Bacardi rum isn't just a technical achievement, it's a philosophy. Every step, from selecting molasses to filtering the final spirit, is guided by an obsession with drinkability. A Bacardi rum should be mixable, approachable, and endlessly clean on the palate. Jack Daniel's begins with a precisely controlled mash bill of 80% corn, 12% malted barley, and 8% rye. The grains arrive in massive quantities by rail and truck and are stored in silos before being milled on-site in Lynchburg, Tennessee. Corn is cracked into coarse grits. Malted barley and rye are milled finer. The grain is moved pneumatically into huge stainless steel cookers where it undergoes a staged cooking process. Corn first, cooked at a high temperature to gelatinize the starches, then rye, then finally malted barley is added as the mash cools to around 65 degrees Celsius. The malt's enzymes convert starches into fermentable sugars. The resulting mash is pumped into one of 64 fermentation vats, open-top tanks made from cypress wood, some more than 80 years old. These vats each hold around 40,000 gallons. Jack Daniel's uses its own proprietary yeast strain, maintained and propagated internally since the early 20th century. Before yeast is pitched, a portion of the previous day's fermented mash is added to the new batch. This sour mash technique helps control the pH and microbial stability of the fermentation environment. Yeast is pitched in liquid form and begins consuming sugars, producing ethanol and CO2. Fermentation lasts 4 to 6 days. The mash foams, bubbles, and gives off heat. During peak fermentation, tanks require constant monitoring for overflow and contamination. Automated sensors track sugar depletion, CO2 output, and temperature curves. Staff monitor the aroma, foam height, and microbial activity daily. When fermentation is complete, the liquid contains roughly 7-9% alcohol by volume. This distiller's beer is pumped into column stills, massive stainless steel and copper columns more than 40 feet tall. Jack Daniel's uses a single-stage continuous distillation process. Beer enters the column at various levels, while steam is injected from below. Alcohol vapor rises, separating from heavier components. The alcohol vapor is routed to a doubler, essentially a pot still operating at atmospheric pressure, where it's condensed, reheated, and distilled again. The resulting clear spirit, often referred to as White Dog, emerges at around 140 proof. Before aging, Jack Daniel's performs its most defining step, the Lincoln County process, or charcoal mellowing. This process takes place in vats over 10 feet tall, filled with sugar maple charcoal. The charcoal is made on-site by stacking 2x 2-inch thick maple planks into long rows, igniting them with high-proof whiskey and letting them smolder until fully carbonized. Once cooled, the charcoal is ground into chunks and loaded into mellowing vats. The White Dog is slowly trickled, drip by drip, through 10 feet of charcoal, taking 4 to 5 days to pass completely through. The charcoal removes fusel oils, aldehydes, and other harsh flavor compounds. The process is gravity-fed and unpressurized, requiring a consistent flow rate to maintain quality. The resulting spirit retains its proof, but emerges smoother and cleaner, with noticeably reduced volatility. Once mellowed, the whiskey is moved into new, charred American white oak barrels, coopered at Jack Daniel's own barrel-making facility. The staves are air seasoned outdoors for 6 months to 2 years, then assembled, toasted, and flame charred to a specific level designed to maximize flavor extraction and color development. Each barrel holds about 53 gallons. The inside is blackened from charring, and the wood sugars have caramelized. Barrels are filled at 125 proof and rolled into one of 90 plus barrel houses across the Lynchburg area. These rickhouses vary in size and construction. Some are multi-story wood frame structures, others are steel clad, but all use passive temperature variation to promote aging. Inside the barrel house, environmental conditions vary dramatically. Upper floors reach 100 degree F+ in summer, encouraging evaporation and faster aging. Lower levels remain cooler and more stable. Jack Daniel's does not rotate barrels between floors, so aging is not uniform. Instead, blending later equalizes the flavor profiles. Barrels are stacked on wooden ricks, often 6 to 7 high. During aging, the whiskey interacts with the wood. Alcohol penetrates the staves, extracting vanillin, lignin-derived compounds, tannins, and hemicellulose breakdown products like caramelized sugars. Oxidation occurs gradually as oxygen seeps through the porous wood. Angel's share evaporation causes the proof to rise over time and concentrates the flavor. Each year, a barrel loses 5% of its volume to evaporation. Maturation time varies by product. Old No. 7 typically ages for 4 to 6 years. Higher end expressions like Single Barrel or Sinatra Select may rest for up to 8 years or more. Throughout aging, barrels are sampled periodically. Staff draw whiskey using a thief and assess it by color, aroma, proof, and mouthfeel. No age statement is printed on standard Jack Daniel's because blending is used to maintain consistency, not target a specific age. When deemed mature, barrels are dumped onto a stainless steel trough, filtered through mesh screens to catch char, and moved to batching tanks. Here, up to 200 barrels are blended into a single batch. Before bottling, the whiskey is chill filtered, cooled to near freezing, and passed through paper or cellulose filters to remove fatty acid esters that can cause clouding in the bottle. For Old No. 7, the spirit is then diluted to 80 proof, using demineralized water drawn from the same cave spring used for mashing. Other products, like bonded or single barrel proof, may be bottled at higher strengths or without filtration, depending on the release. Bottling takes place on high-speed automated lines. Empty bottles are rinsed with pressurized air or filtered water. Filling machines dispense whiskey using gravity-fed nozzles or vacuum-assisted pumps. Bottles are capped with aluminum closures, corks, or synthetic caps depending on the SKU. Labels are applied using roll-fed labelers with electronic eyes that verify positioning. Lot codes and production dates are printed in UV ink or laser etched onto the neck. Every bottle passes under fill level sensors and automated cameras. Defective units are ejected immediately. Bottles are grouped into cases, shrink-wrapped, and palletized by robotic arms. Finished goods are transported to climate-controlled warehouses. Logistics teams track SKU distribution globally. Jack Daniel's is shipped to more than 170 countries. Each batch must meet regional regulatory standards. Export whiskey may require separate bottling or labeling runs to comply with EU, UK, or Asian labeling laws. Quality control labs sample bottles from each run and perform gas chromatography and spectrophotometry to confirm chemical composition. Sensory analysts run blind tastings daily to validate flavor accuracy. Any deviation from the flavor profile, too much wood, too much sweetness, excessive ethanol burn, results in a hold or rework. Spent grain from mashing is pumped to presses, dried, and sold as cattle feed. Wastewater is treated on-site using anaerobic digesters and aerobic ponds before being discharged or reused. Energy recovery systems capture steam from cooking and distillation to heat water for fermentation tanks. Charcoal from the mellowing vats is replaced regularly and either regenerated or disposed of as biomass fuel. Spent barrels are sold to Scotch distilleries, hot sauce producers, and breweries for secondary use. The cooperage also reconditions barrels for use in cask-finished products or special editions. The distillery operates under strict federal and state regulation. Every barrel and bottle is tracked with a unique serial number. Auditors inspect warehouse records, bottling logs, and inventory counts. The distillery maintains TTB-compliant records for every production step, from raw grain receipt to final export certificate. Barcodes and RFID tags on pallets ensure traceability from distillation to retail shelf. Security is tight, bonded warehouses are sealed, and access is controlled. Jack Daniel's uses SAP-based systems for production scheduling, batch tracking, and global inventory management. Brewing, fermentation, and distillation data are logged automatically by PLCs connected to SCADA systems. Operators monitor process parameters in real time on touchscreen interfaces. Alerts are triggered if mash temperature, fermenter pressure, still output, or bottling line speed moves out of range. Scheduled maintenance is performed weekly. Sensors check flow rates, valve positions, CIP cycle effectiveness, and tank volumes continuously. Yeast propagation is handled in a sterile lab with HEPA-filtered air, jacketed tanks, and strict aseptic technique. Each batch of yeast is cryogenically preserved and banked in long-term storage. Lab staff test yeast for viability, contamination, and fermentation performance. Infection events, such as wild yeast or lactic acid bacteria, are rare but can halt production for full CIP sanitization of all affected equipment. Sanitizers include caustic soda, peracetic acid, and steam. Safety inspections and confined space protocols are rigorously enforced, especially around fermentation tanks, high-pressure steam lines, and ethanol vapor zones. Mash cookers and fermentation tanks are cleaned between every batch. Distillation columns are stripped and acid washed quarterly. Mellowing vats are emptied and replenished every few months. Barrels are inspected for leaks before filling. Leakers are flagged and re-cooped or discarded. Every floor drain, gasket, and pump seal is part of a scheduled inspection checklist. The entire facility is USDA certified for food safety and operates under HACCP protocols.